got the shipment and the rental gear, and I've got to coordinate with the rental company to come pick it up tomorrow morning. And then I figured I'd come in the morning just to make sure if there's anything we need to do to make sure our stuff gets shipped out correctly. The, the work here, to be here with B for that. And then I'm going to try and get an earlier flight because I booked myself on an afternoon flight, not knowing if I would need to be here longer, but I don't think I do. Here, up, monitoring the attendees.
Yeah. If someone pops up, I'll be right here close.
Hey Raymond, good morning. This is John. How are you today?
Hey, John, can you hear me?
Yes, sir, I can. How are you?
Great, I'm good. How are you?
Good, thanks. We're waiting for the presenter to log in. Oh, he just did as an attendee. So I'm going to
If
let
you're
him.
speaking, you might be a little on the quiet side.
Okay, is that better?
Yes, that's a bit better.
Okay. All right. Yeah, our panelist, Jurgen, just logged in as an attendee. So I'm going to go over and promote him to panelist. And we're going to check out his video and slides.
Yep, sounds good.
I'm going to do that. Thank you. Wes? I thought you were correct. He's in? Good morning, Jurgen. This is John and
Okay, hello.
Perfect.
I'm fine. You're again in Cologne. I'm still getting everything set up. It will be more quiet in the once we start the meeting.
Okay. We wanted to. We will be running your slides.
Okay. I just want to figure out on my side actually just 1 second. Jonas, Arthur, kein Fußball hier. Könnt ihr bitte jetzt rübergehen ins Zimmer? Ich muss hier kurz was ausprobieren. Ihr könnt gleich wieder kommen. Haus.
Arthur, komm, lass Monopoly spielen. Ich bin Pinguin.
I want to figure out on my side the best audio setting, whether I use the headset or not.
Best audio setup.
So I don't know how well my voice is coming through now. Ja, dann gehen wir drüber. Okay, dann musst du kurz bei mir bleiben. Komm her. Ach, gut. Was willst du spielen? Das hier?
Ja, das hier. Das will ich hier.
Yeah, I can just do it through my audio. Yeah. Jurgen, yeah, we've got audio, we've got video, and we'll be running your slides. So we're in. Yeah. And we need you in about an hour and 15 minutes for your panel.
Hi, John. Top of the morning to you.
Hey, Cheryl. Stand by for a moment.
Absolutely.
Jurgen, if you can unmute, I muted your mic for a moment. You can turn them
Okay, just checking. So now I'm actually using the computer without any headset or microphone, just the built-in. I don't know how well that comes through in terms of the audio.
It comes through pretty well. If you had a dedicated mic, it's always stronger for because the remote audience.
Yeah. So let's check that setting.
Much better. Yes, that sounds really good.
So now I'm on the headset. I don't know if.
Yeah, that sounds much better.
It's better. Okay.
Yes.
So then I'll use that setting for later.
Much more clear.
Okay. Perfect. I'll just leave that connected then. And yeah, you have my slides.
We have your slides. We'll be running them.
Yep. Perfect.
Hey, John.
Can you hear me okay, Jurgen?
I can hear you. Sorry. Oop.
John, you are very faint on Zoom. I'm sorry to
Very
report.
faint. Okay, I'm literally holding the microphone to my mouth.
Well, now it's fine. It was more faint before.
It's better.
It's still pretty faint, John. I'm sorry.
It
Yeah,
It is okay. Garrett, is there anything you can do? They're saying I'm very faint, and I'm holding the mic right here. So
yeah, if you speak like that, it's all perfect. It just seems to go a bit on and off. Maybe it's when you move your head or something. I don't know.
I'm holding it so close that I'd be surprised if it's. I'm hearing myself a little bit of loop back through the Zoom attendee. I'm monitoring on a different workstation, and it does sound low.
Are you potentially like picking up from a different microphone than the one you're holding?
Let's see. I'm on Dante, so my microphone. I'm coming through to you, right, Garrett? Okay, so my microphone on Zoom is Dante. You know, I know we were getting this complaint yesterday that things were coming through low and they were booming here on our audio system. So we're just going to take a look to see if there's something in our settings that isn't working as well. But Jürgen, we do have your slides. We need you in about an hour and 10 minutes. So if you want to mute,
Okay,
take care of other things, we'll be fine. We'll be good to go. We just wanted to test with you while we could.
I will do, and I will set up a bit here in terms of the background, and then I'll be back online in about an hour.
Great, thank you. So Cheryl, I'm going to keep talking just because this worries me. I know we were getting complaints of low audio yesterday on the Zoom, and I can
Yeah.
see on my Zoom audio settings that
Yeah, it's not,
the deflection of
you're
the
not
input
too
level,
loud.
yeah, the deflection of the input level is low, and I'm holding the mic right to my mouth, and I'm talking at a pretty good level. So that worries me that there's something in our audio chain that's knocking it down. That's the only thing I can think, because we've got plenty of sound coming out of our audio console going into the room, but somehow on the Zoom it is low.
How can we help you in this moment?
Oh, just by monitoring, Cheryl?
Wow, already an improvement.
Oh, an
Keep
improvement.
going.
Keep going. More if you can, Garrett. Cheryl heard a noticeable improvement in my sound. So I want to make sure that we're getting the strongest signal out we can. It just looks weird on the, you know, the little Zoom audio meter that it doesn't deflect. It's deflecting a little more now, but I am on the mic and I'm speaking in my, you know, microphone voice. So I'm used to, like on my MacBook where I'm in as an attendee, I can hear the return audio. And yesterday I was able to turn it up like halfway to monitor, and it was coming through strong. If I turned it up all the way, you know, it was very clear. So still could use more if we can get it, Garrett. Just want to make sure we get the best audio out there that we can. And it just, I can't explain it because I know normally when we plug these devices in, they're feeding a pretty strong signal into the computer.
Right. You know what was interesting yesterday was that the sound at the podium was good. It was at a good level. But when we transitioned to the hand mics, it was the hand mics that were really.
Okay, so yesterday the podium. How about the table mics, Cheryl? When people were doing the panels, how did they sound?
The table mics also sounded faint.
Okay. So the podium mic,
But the hand mic
clear,
was
but
the
hand
faintest.
mic and the table mics were a little low yesterday, Garrett. I don't know what would be different in our setup. Yeah, he said this isn't making sense to him because he's got everything in his console all routed pretty much similar, you know, all the setups are the same. But let's keep working it. Give me just a second.
You guys are doing great work over there, and we very much appreciate you.
Thank you, Cheryl. I know you and Raymond are managing the other stuff very well at your end. Everybody's very happy with day one, so looking forward to day two being just as successful.
That's what I was just looking at, and everything on Dante is fine. So, so the tabletop mics and the podium were fine.
No, just the podium. That was the best. She said the tabletop mics and the handhelds both sounded faint.
Was Cheryl on all day?
Yeah. You know, she said you could hear, but you had to turn it up. So that was your experience yesterday. The table and the handhelds came through, but you really had to turn them up to make them clear. I'm turned up pretty. Went away. There we are. Check 1 2. Check 1 2.
I was making sure we sent it.
Okay.
So I muted the output.
Yep. Okay. That's deflecting louder on my audio panel. Cheryl, is that sounding different?
Yes,
It
yes.
sounds much better. Yes.
Yeah, John. It sounds way better now.
Yeah. What did you do? Oh. Okay. There's something on the console we think is clipping the channel and making it lower. Yeah, because I'm seeing a much different level over here, and I'm hearing it. Everybody online said it sounds much better now. So, do you think that was happening to the table mics also? Check 1 2. Check 1 2. Testing 1 2 3. Let's see. It's 8:35, so we still got a little time before we start. We do have 9 attendees in, so they're getting the benefit of hearing us do a Zoom test. But the program will begin at 9 Pacific time. So the console, you think there was some setting that was clipping on the mics? As that does.
I just boosted the level.
Okay.
So it's
Yeah, I hear it. It sounds clearer. Do you want to test one of the table mics to make sure we're getting the same result? Was that like on a group, or was that on an individual mic?
the table mics.
Yeah, are they in the same group? All right.
So I boosted all of it going to the same.
Okay. All right. Do you want me to walk up and test one of them? Okay. Guys, I'm going to take this mic, but I'm going to walk up and test one of the stage table mics. So you can give me feedback, tell me if that sounds good also.
Fabulous. Standing by.
I'll do the podium first, just for fun. Podium mic, test podium mic, check 1 2 3.
Sorry. Little low there.
Garrett, podium mic sounds low. Oh, that's better. Yeah, that's coming through. That's got to be better, Cheryl, because I'm hearing it in my headsets.
Whatever mic you're using right now is great.
That's the podium.
Okay, podium sounds good.
Good. Table mic 1 2 1 2
That
3.
sounds good.
Next table mic, test 1 2 3.
Excellent.
Table mic, test 1, 2, 3.
Phenomenal.
Table mic, test 1, 2, 3.
That one is a little low.
That one's a little low, Garrett. Testing 1, 2, 3. Testing 1, 2, 3. That's good.
Better. Yes?
Yep. And fifth table mic. Testing 1, 2, 3. Testing 1, 2, 3.
5 sounds good.
That's all of the mics.
All right.
So we're better. Thank you for your help. We're not quite sure what was happening with that level going through our Dante system, but it sounds good now, Garrett. Thank you. Okay, I think we're squared away. We'll go back to music and get ready for show start at 9 o'clock.
Thank you, John. When are you, is the live stream up as well?
Yes, we started the
Okay.
live stream. Caesar and I started that earlier.
Oh, good. Going
Just to
out.
make sure everything was working fine. Everything's going out. And of course, we're live on the Zoom now also.
All right. Excellent. Excellent.
All right.
Have a wonderful day,
Everybody have a
team.
good show. You too. We'll talk to you later.
Thank you.
You know what?
Oh, I guess is that large?
No,
I guess it's not that large.
it's not that large. It's still megabytes.
Yeah. Jamie said very large.
You do hear me? Oh.
Hello. Good morning, everybody. We're going to get started in about 5 minutes, so if you need to refresh that coffee or grab some breakfast, go do that now, and then come straight back. All right, morning, everybody. If you could please take a seat, we're going to go ahead and get started with day 2. Good morning. Is everybody awake? Thank you. Who said? Oh, it was Mike. Thanks, Mike. Good morning, Mike. Welcome. I just want to do a few reminders. I know you're pros at this because you were here. Most of you were here yesterday. I hope you have your program still, right? It's probably not as cute as mine because I put star stickers on mine so I can find it. But just a reminder, on pages 3 and 4, we've got a lot of really good information on there. It's got the Wi-Fi directions. It has a floor plan of the student union so you can find your breakout session later today. And it also has the links to Slido. So reminder, Slido is how we submit our questions. That gives everybody, both in person and virtual, a chance to submit questions, and you can upvote them. It's really fun. And then during the breaks, I want you to go and look at the poll tab because, just made me much louder. Thank you. On the polls, we'll have polls for every break, and we'd really appreciate your responses. So, lunchtime, we're going to have UNLV lab tours again. So if you're interested in going on a lab tour today, please sign up for those by the end of the morning break so that they know how many people to anticipate. And we'll give you further directions at lunchtime. And also, there's a mother's room upstairs in room 315. You will check in with the receptionist if you need it, and they will give you access and make sure the door is locked. Okay, so today's lineup is a really exciting one. It starts on page 8, and we have panels on proving grounds, technology infusion, and space sustainability. Lots of really interesting conversations going on within our LSIC group at APL. And then we'll follow up with breakout sessions that are really based on all the panels from both days and gives you a chance to ask additional questions. But first, we're going to bring this back to the whole point of this, which is the human exploration aspect and getting humans to the moon. And I have the distinct pleasure of introducing astronaut Andre Douglas. Prior to being selected, he was one of us at APL. Woo-woo! So our LSIC team was super excited when we found out he was coming back. At APL, he worked on maritime robots, planetary defense, and space exploration missions, as well as LSII. So he was there with the dust mitigation team right from the start. And he was then selected by NASA as a member of the 2021 astronaut candidate class. I won't go through his entire bio because I don't have enough time. I only have 5 minutes for everything. But it is online, and he's a very impressive individual. But without further ado, I would like to welcome Andre up to the stage to come and talk to us about human exploration of the moon. So here's your mic. Push that back.
All right. Good morning, everybody. All right. It's good to be here in Las Vegas, but honestly, it's good to be here back at LSIC. I am so happy to be here and see some familiar faces. It's like a nice reunion, but the main reason why I'm here too is to really share what's going on at NASA from a human spaceflight perspective. So for the presentation today, I'll talk about my training program and Artemis, what's going on with me and how we're going to the moon, right? And what you guys can do as far as ideas and ways to contribute. So we'll go next slide. Oh, I have it? I have it, nice. All right, cool. So to begin, I usually talk about me a little bit, try not to go through my bio. I appreciate that because we'll be here for a while. But in general, Andre Douglas, NASA astronaut, graduated in March of 2024, so I have not been up in space yet. We just graduated. Our training program, when you are an ASCAN, an astronaut candidate, really consists of 5 major elements. So I got 2 of them up here. The first is flying the T-38, which is a lot of fun. Helps us understand crew resource management, how to work as a team, how to go through checklists. All that stuff's super important for when we're on the launch pad trying to get ready to go to space. And then the second thing that we do is we practice spacewalking. So spacewalking is really fun. You know, we're in this huge pool, the neutral buoyancy lab. We're trying to figure out how to do 150-page procedures, trying to figure out how not to pee in a diaper and, you know, worry about how to pull muscles and figure out how to, I love the way Anne McLean said it, do brain surgery on the side of a cliff, right? You're doing all of this technical work and you're managing a bunch of tethers and it's really challenging. But for me, I really like it because I really can't stop moving. I can't stop thinking. And this is one of those full body experiences that, you know, we really train for as astronauts. It's one of the pinnacles of our training. So the other three things that we do, we speak Russian, we fly the robotic arm, and we do a lot of the ISS systems training. So when we graduate, we're pretty much ready for the ISS. But when you get selected for a mission, specifically ISS, you're basically going to do all that all over again. So it's like a 2-year period of training. So it's a lot of training. But I'm going to try to blast through this a bit because I want to get to some of the technical things that we're working on at NASA. So if you have questions, kind of save them towards the end and we'll do Q&A. All right, so a little bit about my background. Also a Coast Guard officer. Right now I'm in the Coast Guard Reserve as a commander, but I started off my career doing Coast Guard operations down in D7. This is out in Florida, and we did search and rescue operations, migrant operations, a lot of helicopter operations, trying to make sure we protected our borders, you know, anti-drug operations. It was a lot of fun. I got a lot of leadership in, led people, and did a lot of dangerous things. So that really helped me out with my operational experience to be able to join NASA. But, you know, I really also give credit to APL because, you know, one of the things with NASA that I appreciate is it's very technical. And for me, I always wanted to be an astronaut since I was 7. So when I was in the Coast Guard, I got my operational experience, but I was like, hey, I really want to get really deep in my technical experience. So I actually went into the reserves after the Coast Guard and went to APL. And so I was in the reserves while working APL. And when I was in the Coast Guard, I actually became a naval architect for the Coast Guard. So I ended up working at APL in the sea control sector, right? So that was where they needed help with submarines. So we had a lot of submarine work. There was like the submarine ballistic missile launching system, where we basically instrumented that system and tried to figure out how to interact with robotics underwater, which is the wave glider that you see in the top left. So there was a lot of unique things that we were doing there that was operationally driven and engineering driven. It was pretty cool. So the other thing on that slide was the planetary defense. We talked about, did the space exploration sector as well. DART, double asteroid redirection test, that was a lot of fun. But all that stuff at APL was super helpful for doing all the stuff that we do here at NASA. A lot of fun at NASA. So basically, now that I've finished the training, I became assigned to Artemis II. So Artemis II, I was a backup for the 3 US crew members. And what we're doing for Artemis II is we're doing the launch around the moon. And basically, we won't touch down on the surface. But that's for Artemis III. So for Artemis III, we actually still do analog missions to practice. And one of the analog missions we did was Jet 5. And Jet 5, here I am doing some testing with the suits. We basically do a lot of geology, and it's important to make sure we understand how to map out the time it takes to do the tasks. So all of these tasks are done with using tools and these heavy packs that are about 100 pounds. And we're in the heat, and we're trying to figure out, how does this impact my performance as the human in the loop? How do we simulate how to do this to get some realistic data to plan for all of the EVAs that we're doing? So this was actually a really helpful experience for me because it gave me insight into the mission. Like, I'm a very, very proud engineer, but what I've learned being at NASA is how to understand the mission and the operator and the user. So going through Jet 5 was like very special. We got to go and work together as a team. It was like a mini analog, and we're trying to figure out, you know, how do we navigate using just the cuff checklist and a map book that's on a cart that's super heavy, and you're trying to push this cart, go up and down hills, and try to communicate with MCC, all these things that we're trying to do. And it was, you know, not the exact mission of going down and landing on the moon, but we got a lot of insight is how do we work together and how do we use technology to better, enhance our SA. So in the top left and bottom right, one of the things we did was we did some advanced Artemis EVA runs, and basically we would pretty much put our mission planning system in our eye instead of on the cuff checklist, and I could basically toggle all of the instructions and the images so that I don't have to like stop, flip my map book, and waste time. It was pretty cool. The other thing that was super helpful is the navigation piece that you get in your eye display. So you can get a little waypoint that says like, hey, I'm about 150 meters from my target. Okay, I'm 125, I'm 100, oh, I'm 120, I'm a little bit off course. There are these little bits of information that can really help with the cognitive load and the time and the efficiency, and I think that was super valuable from the advanced Artemis runs to do. So highly encourage a lot of the ideas that come out of these forums and the ways that we can enhance our ability to do the mission. That's super important because it's like $1 million or so a minute that we are on the surface, and if we can save a minute or two, like why not try that? So we can't do that kind of analysis without testing and understanding what are these impacts, and so Jet 5 was a really, really good test for us. So now that I'm assigned to Artemis 2 as a backup, we actually do training for the ground systems as well. I know this is for the Lunar Surface Consortium here, but I still want to talk about training as human in the loop. So on launch day, what we train for is the worst case scenario. We train for, if something's going to happen on the pad, the rocket's going to blow up, how do we get people out of the vehicle? How do we keep people away from the blast zone? So there's this test, it's called ISVV1. It stands for Integrated Systems Verification Validation. And we're trying to validate and verify the system that includes the mobile launcher, that's where the SLS is going to rest on, and then the baskets down to the terminus area, which is blue. It's like a big, like track and field turf where it's kind of bouncy, so if the actual baskets hit, it's not going to crack. Then we have these big tank-like vehicles called MRAPs. They're mine clearance vehicles. And then we have our suits that keep us, dry and cool, oxygen. So this is all integrated to basically get the crew out of the Orion in case there's some sort of a leak, an explosion is about to happen. So it's really important for us to go and demonstrate this. And I did this as a backup with Jenny Gibbons. Jenny Gibbons is the backup for the Canadian astronaut. So Jenny and I worked together on this, really got to understand what it's like to be a crew member, because I got to do the crew member full suited run. And the most important thing we have to do as backups is we have to be the astronaut support person. The astronaut support person is supposed to go in and close out the crew in the vehicle. So we're the last people that the crew sees before they go to space. So it's kind of like a special privilege and an honor to do it. But really good experience for us to understand how things will go on mission day. So the other thing we did as part of a crew, I would say crew of 6, Artemis 4 has Artemis 2 has 4 primary members and then 2 backups. So all 6 of us went to Iceland. Iceland was great because the whole purpose of this was to do geology training. And Charlie Duke and Jack Schmidt said when they got back from the moon that Iceland was one of the most realistic places here on Earth that we have. And I'll tell them that I haven't been to the moon, but like I felt like I was there, and it was pretty cool. It was really neat. We got to really look at a bunch of basalts, similar type of basalts with plagioclase that'll be on the moon at the South Pole that helps us understand how to be very comfortable analyzing that data. So we're looking at far field images, close-up rocks, breaking rocks, hiking around, and it was just a lot of fun. The biggest thing that we do, too, as Artemis 2 is we try to really pave the way for Artemis 3, 4, and 5 for that training curricula. So we go through it as if we're getting trained, but we're also providing some feedback to make sure we got the right content in there. So that was really good. Just some images here of the one of the acid lakes behind me in the right image, and there's a bigger lake in the background too, and a really cool feature that we saw on our 2-day hike in Reykjavik. So again, I'm trying to go fast so we can get to Q&A, so I apologize about that, but one thing here, why the moon, right? There's a lot of reasons why we're going back to the moon. I would say the biggest one is national security. right? We have our science, that's very important, but you know, it's no secret. We're trying to get up there before other nations to make sure we can provide freedom for all, to make sure we can explore as a species. So that's the biggest thing, and there's a lot of other pieces with, you know, enhancing our economy, providing new technology that you see up here, but in general, we're trying to get up there safely and as quickly as possible. And so for Artemis, you know, this is really a, you know, foundation for deep space exploration, right? So we're trying to build this huge network, systems of systems, to get us from here to the moon, to Mars, and beyond. So really, going to the moon is our proving ground to make sure we can do this. So we have to have all these components work together. So the SLS system, Space Launch System, Orion, the VAB, comm systems here on the bottom. We also have other components of the system that will get built upon in the other missions that are in the future. Okay, I hope I didn't go twice. Yeah, so you guys have been seeing a bunch of media about SpaceX and the chopsticks, right? Like, that's important for us too, because that's gonna be our lander for Artemis 3, right? And then Blue Origin's also putting their lander together for, you know, 5, 6, 7. It's great to have two companies work together to make a lander in case one doesn't go well. We have a backup, but we're trying to put all these things together to get us to the moon, stay on the moon. So we got the landers, we got the comm navigation systems on the ground again, we got our spacesuits. We also have a bunch of rovers that we're working on that I'll talk about. Then we got our new space station, which is the gateway that's going around the moon. So there's a lot of pieces that are going on, and it's challenging because, you know, each of these, they get in development, you know, every year and a half, 2 years, right? And so the requirements that you set way in the beginning may get iterated upon or learned upon, however you want to call it, and that makes it really tough for people. But here are some of the missions. Artemis 1, we had 2022 unmanned, and that was successful. Artemis 2, that's the one I'm on as a backup, backing up the crew here. We'll talk about the crew in the next slide. Artemis 3 is our first, you know, EVA bunch that we'll do for Artemis. We've already been to the moon on Apollo. And then Artemis 4 is the gateway, so that's the new space station around the moon. And then Artemis 5 is when we're gonna have the lunar terrain vehicle operate, and that's also an interesting project as well I'll talk about. Here's Artemis 2 crew. On the left, we got Jeremy Hansen. He's a fighter pilot for Canada. Reed Wiseman is our commander. He's a Navy test pilot. Victor Glover is another test pilot, and Christina Hammock, also former APLer. There's a trend here, if you hadn't noticed, but she's awesome, and I think she was in the space exploration sector too when she was at APL. But all of these humans here are great people. I mean, it's a family. We're pretty tight, and I want to stress this because I want to thank everybody here for what they're doing, trying to make sure we come back safely, we get there safely. We got families, we have people we love and care about. We care about you guys, but like, we understand there's a lot of things going on to make this work, and it's not easy, but you know, we just thank you guys for trying to think of the right solutions and do things the right way. So as far as the components that I talked about, Gateway, this is pretty interesting. You know, we have multiple nations involved, NASA, JAXA, ESA, we got Canada, everybody's coming together just like the ISS. So it's important for that team collaboration and to be able to work together to do this. But in addition to the nations, it's not just them. I mean, we have contractors that are also supporting, and there's a lot of different moving pieces, as you can see, right? So we got the nations, but we got Boeing, we have Grumman, Aerodyne Rocketjet, we got, you know, Maxar, SpaceX, like there's a lot of people involved, right? So there's this ecosystem of folks that work together to make sure we can get this done. And there's some interesting challenges with, you know, Gateway in general. There's like, you have these solar arrays, and I would say Gateway is much smaller than the ISS. It's hard to see to scale. I don't have a scaled image or anything, but it's smaller. And you can imagine, you know, we have these solar arrays, and we have docking challenges where, you know, you have this large potential SpaceX vehicle, right? That's the lander that's supposed to go up and dock to this thing, but then we have to worry about, you know, plumage and not hitting the solar arrays. That's gonna be pretty interesting. We also have a new airlock that's being built by the UAE, and that's gonna be pretty cool. But the UAE is also new to the game, right? You know, they have to make sure they work well with us to understand the requirements, the past history, all the training and things that we've done. So again, it's great to have a bunch of people working together to make this happen, but we have to be very, you know, careful and diligent on making sure all the details are met. All right, and so for the advanced suits, I kind of mentioned a little bit of this in our, you know, in the Jet 5 discussion. And again, the Jet is really the joint EVA test team. We do this every other year or so to make sure we can iron out the con-ops of what we're going to do on spacewalks. But for the suits, you know, we have Axiom right now. They're building our new suits. You know, the ISS suits for what we wear today, the EMUs, those are about 250 pounds. And then these new spacesuits, they're going to be about 450 pounds, right? It's a lot of mass, right? We'll be 16G on the moon, but there's a whole new, almost mobility aspect of how we do things, right? So all the stuff we did out in the field for geology, you know, hammering away at rocks and trying to move the cart uphill really fast, you know, we got to understand and somehow test before we get there what it feels like to be in a 450-pound suit. Again, 16G, but you still have inertia. So how do I go downhill and stop without falling, right? There's a lot of little things from a human side that we have to understand. And one of the biggest things, too, that we're trying to figure out is how do we do an incapacitated crew rescue, right? Like if I'm doing this 450-pound suit, I tweak my knee, my meniscus tears, and I can't get back up, how is somebody, my partner, going to drag me 2 kilometers, put me in the LTV and go when the suit is 450 pounds, right? So think about all of those things and what we're trying to do at NASA. And I'm hoping as we network today, I start bridging people between LSIC and NASA to figure out where are we at NASA, what ideas are out at LSIC to make sure we can make this happen. But it is not an easy task. So the other thing, I'll also have a go back. I think I can go back on this. I want to mention for Gateway. So Gateway, like the ISS, one of the things we're also trying to figure out is how do we come up with clever ways to do any sort of incapacitated crew rescue. So for Gateway, right now, the plan is not necessarily to do a lot of EVAs, right? Not to work on the Gateway system from the outside, because we're going to have a Canadarm number 3 to do a lot of the robotic work. But as we know, ISS right now is working beyond its service life. We're doing a lot of repairs that were unplanned because we've extended that life. So we can see that Gateway is likely going to have something similar where they unfortunately might not have planned to do EVAs, but will probably do EVAs. And so if we do that, what kind of rescue systems can we think of that might not be built into Gateway right away? So if like ISS right now, we basically have a bunch of tethers that help us come back to the airlock if we ever fall off station, and they kind of retract, but it's kind of tricky because if you fall off station, you know, you can drift around, you can bang up on things, and again, 250-pound suit. So they have something called the Safer, which is a little jetpack that we have to rescue ourselves, right? If we come off station, we can fly back to station with a hand controller. And so that's all great from ISS perspective, but none of that, I think, is being built right now because there's no requirement for it, because we're trying to say, hey, we're not going to do EVAs for Gateway. But again, like, we need to be somewhat smarter about having solutions for these things as we anticipate, you know, us doing EVAs in the future. At least the crew office thinks we will be doing that. You know, the other folks may not. So just something to think about. Then for lunar terrain vehicles, you know, this is an interesting one too. Right now we have 3 contractors trying to basically win this contract. They're in a 12-month sprint phase to do prototypes and a bunch of HITL testing. And so that's important to make sure we have confidence in the designer and that they have realistic deadlines. And so LTV is basically going to be the dune buggy, where you're not pressurized in the vehicle, but you're wearing your suit. So you're, again, 450-pound suits on the dune buggy doing operations to extend our range. And it's also interesting because right now, the goal and the deal is 30 days out of the year, we're using it as astronauts, and the other time, right, the other 11 months of the year, it's being driven robotically, right? And there's potentially robotic arms and manipulators to be used to explore the moon when we're not there. And so there's a whole nother aspect of, well, who controls the robotic arm and the vehicle when NASA astronauts are not there? How does MCC get configured? Where do the controllers sit? Are they sitting at NASA? Or are they sitting at their site? So there's a lot of things being worked to figure out what does the architecture look like for that when we're sharing a vehicle for so many months out of the year. And then same thing for pressurized rover. So pressurized rover is interesting. This one is where you are pressurized inside the vehicle without a spacesuit as your normal operations. And this, you're supposed to be living up to about 30 days or so in the vehicle. Very interesting vehicle. I was actually in Japan last week because JAXA is building this. They're working with Toyota. So Toyota builds cars. They're building the rover and their space agency. And so we went out there to kind of collaborate and understand the design and all of that stuff. So it was really interesting. They have, talk about cool technology. Inside the rover, it doesn't look like this right now. This is an earlier rendering. But they have like 2 windows in the front. But you can put screens down on the inside. And basically, there are 8 cameras around the rover that has a ability to take the environment in and then project it on a projector screen inside the vehicle. So when we drive, we're actually using video to see everything in front of us, behind us, and it's really neat. But there's a lot of things that we're curious about and want to make sure that we understand fully before we try to go down that path. So as an astro, I went down there to kind of understand how does the motion-based platform feel with this, you know, hopefully not delayed image that, you know, ideally matches up with the motion that I see, but we don't have translational capability yet, just roll, pitch, yaw as we're running on the terrain. And so there's a lot of innovation, which is great, and we encourage that, but we want to make sure we're not thinking about or we're missing the basic needs of the operator. So, you know, if they want to get rid of windows altogether and rely purely on a camera system, we got to think about, okay, well, this 10-year service life vehicle, how often are those cameras going to go down? And am I willing to drive this vehicle 7 kilometers from the lander and then the camera break and then I can't get back and I'm going to run out of oxygen to be able to get rescued? So there's a lot of things that we're trying to do as a crew office to make sure, you know, we are vetting the systems. We don't want to hold people back, but we want to make sure we collaborate together. So just some examples about what we're working on here. And so the other thing is, you know, for the Artemis Accords, there's like 40 countries that are with us. I think we have like 5 or 6 more since I've done this brief. So really we're trying to bring all of humanity with us. And then basically back in Apollo, we came in peace. And then for Artemis, we're returning for all of humanity. And so I kind of end it there. I talked a lot. I love to talk and keep going, but I want to make sure there's time for Q&A. Thanks.
Can anybody hear me? Ooh, we're gonna have 2 options for Q&A today. We are doing Slido, but if you'd like to ask something in person, let me know and I will run a mic over there.
Oh, hello. Check. Oh, great. We've got audio. All right. So we've got a bunch of questions in Slido. I know Jamie's going to be the wandering mic trying to get some from in the room. But we'll start with a question that was top most upvoted so far. What test environment do you wish existed but doesn't yet?
Great question. Oh, man. So I think be nice to have a full kind of field that has for the moon, the regolith and the boulders and the terrain, because you know we do a lot of thought exercises and concept development in a vacuum at the desk, and we don't have kind of like a full driving range yet, and I think there's some being built. I know there's some stuff going on at A&M. I know even over at ESA, they're working on this really interesting full-blown indoor rover simulator environment. It's really like a test bed, not a simulator with computers, but a full-blown almost arena So I'm looking forward to that because you would do the rover type stuff, but you could also integrate with the suits and the rovers, and then you could probably do some practice geology there. And so I think having all of those pieces in one place to flesh out the architecture of what we're doing would be wonderful. An example would be, right now we're trying to figure out how do we prevent rovers from hitting astronauts when we're doing, let's say, proximity operations. We have a rover that's being controlled by a commercial company somewhere else, and nobody's in the rover, but I'm an astronaut probably about 7 feet away, and we're doing some geology, and then we want to test out how do we do kill switches, right? How do we say, okay, test that when you're within 3 feet of an astronaut, you're not going to run over their leg. I think there'd be a great use case for that type of facility to do that full-scale testing. I just haven't seen it yet.
You might want to stick around for the next panel, by the way.
Great.
It's on Proving
wanted to
Grounds.
come
We'll
here.
talk about a lot of that.
Awesome.
Jamie, do you have a question from the audience? Or I've got plenty here too, so I'll keep her, Jamie will keep moving around. And you can raise your hand if you've got a question you want to ask Andre. Next question we have, really highly upvoted, is are there any technologies or component systems that would make your job easier or safer?
Yeah, so I mentioned this in Jet 5 where we were doing our 4 EVAs, and whenever we're doing our science tasks for geology, we would try to make sure, or the ideal thing would be to have some sort of a robotic system or a helper that does some of our, I would say, repeatable tasks that we could offload ourselves so our cognitive load focuses on the science. So putting out like sample markers down, instead of me going down and doing this in a 400-something pound suit, and if I had like a little mini rover that went out and just placed them, you know, put a little in my heads-up display, I could look at a target and like blink and mark a waypoint, and this other little rover would come over there and do that. Like that would be pretty cool because I could do all that while I'm walking over to the tool cart, prepping my tools, and it's this, you know, robotic human interaction that's at a really complex and unique scale. And I would say that's not trivial, right? So I don't want to ask for that and then we don't get to the moon because we're trying to spend all this time and money. But if I mentioned earlier that, you know, a minute is like X amount of millions of dollars, we would start doing that study in that ideal field that we were just talking about that we might hear about to see what that trade-off would be. So that's something, at least from science, I would say gathering function that we're trying to do would help. And then the bigger thing that would help too, having some sort of GPS on the moon, call it cheating, but hey, if we could get a constellation up there to help with SA, geolocation. There's also a few things I saw with, you know, people were talking about maybe building these very tall solar panels, another company that I won't mention, and it'd be interesting to see like if you could integrate some sort of a geolocation device at the top and you had this grid of solar arrays that help power generation. Like that would be neat to give us beacons to get back to lander when we're doing our EVAs, to help with position, like all that type of stuff. The other thing that's interesting that we're finding tough is when you're doing your rover ops, how do you get video while driving, right? Like, do you build this complicated antenna that's gonna track towards the lander? Because that's the only way we can get our video back as we're doing all these donuts and going crazy on the moon, right? But honestly, like, we don't have a way to do the video in real time and bring the Earth with us when we're exploring, right? And that's, I think, important. But again, we could still do the basic mission without it. But if there's opportunities to get, you know, some low-hanging fruit, again, that's not trivial, but that'd be nice.
Awesome. There's a question, I think, in the room. Jamie, are you on your way over there?
Go, Jimmy, go. Go, Jamie, go. This is why I asked. I was like, Jamie, you sure you want to run around?
We do this every year. We get around. We have fun.
Awesome.
Thank you, thank you.
Hi, how's it going? Thanks for being here. Bryant Beeler, Doctor of Technology. You mentioned multiple like cognitive automation and cognitive load balancing tools, as well as some like human machine, human robotics, human machine teaming capabilities. What are the best ways to get those capabilities in front of you or in front of the right people so you as the end user can check them out and say this would be helpful, this would not be helpful? Very similar to this like Q&A that we're having right now.
Yeah, that's a great question. I'm not too sure about the formalities, but what I remember from at least Jet 5, which was that big test that we did in Arizona, was they had tech demonstrations of the advanced EVA runs where I was looking at like this inertial, this IMU that would help me with my position, and a few other companies would have other LiDAR type sensors. And so for me to be on that test and see the difference of without the technology and with the technology, how valuable it was, that was great. But I'm sure there's a pretty rigorous process to get there. And as far as like, if you can catch us on the fly, I mean, we are an office of nearly 48 or so, and we're going in a lot of different directions. It's hard for us to take time to see things. So I would say it would be mainly up to us to try to get with our engineering groups, and if you guys have connections with the engineering groups, which is what I'm trying to do today, they can help filter what would be of value to us, because a lot of folks in our engineering groups, they also do NBL runs and they also do astronaut type things, so they can get our perspective, and then they would then bring it to us and say, hey, like this is something that is worth looking into, and then also they request our crew time, because our time, like anytime we have something to focus on, like it has to get requested by our office. So like for me personally, like what I like to do is, you know, I'll be on LinkedIn and I'll look at things and I'll thumbs it up and I'll say, oh, this is great, but that's just Andre, that's not the office, so I don't want to speak for them. So the official way is we have to get crew time requests to go see these things, but I think your best bet would be to try to work with the engineering organizations and human factors organizations at NASA to get into that ecosystem first, and then it comes up.
Okay, we might have to work together to open up those demonstration events, because I've seen, and please don't quote me, I think it's FathomWorks and NavC having a similar obstacle where they opened up those demonstration events to community and to academia so that the feedback loop can be more iterative, so that we can communicate more fluidly and they're less isolated events. So that kind of points to that direction. So we might have to work on that.
That would be great, because I would love to eliminate the isolated events. I feel like as a species, we come up with similar ideas in different areas, and so the more we can bring them together, the better.
All right, there's a question here that I think maybe hints at something that you have liked before, or maybe they know and have tracked you through your time at LSIC. How have dust and dust mitigation been incorporated into your astronaut training so far?
Yeah, great question. So for what I've done so far, it has not been incorporated because we have not trained for Artemis 3 just yet. So for Artemis 2, we only go around the moon, we come back. We're not doing anything on the lunar surface. We kind of talked a little bit about, actually I don't know that we actually did. So for the analog mission we did for Jet 5, we didn't really go over dust mitigation. We might have talked about it in the airlock. But some of the things that I've been thinking about heavily is specifically that Japanese rover. So think about this, right? This rover, which you saw earlier, is going to hold 2 people, not in spacesuits. The whole vehicle is going to be exposed to vacuum. The whole vehicle is an airlock. There is no airlock between the people tank and the atmosphere. So every time you open that hatch, you're going to do your 8-hour logistics EVA just to move a bunch of stuff from one place to another. And then hopefully your seals are good. Now you don't have dust, you don't have debris and nicks and dings. And so that's the thing that keeps me up at night, even though that's likely Artemis 7, right? It's going to be a while. I'm thinking about that, and that's very important. And so I'm hoping, and I remember this when I was doing LSIC, 3 years ago in dust mitigation, like looking at the ideas from academia, industry about how to, walk through something that blows the dust off, how to, use some sort of electrostatic device to pop it off before you come in, because that's going to be pretty important. And then if we're in Starship, going down and coming back up, like are we bringing that dust to Gateway, right? All that stuff's going to start happening. And so I think for us right now is important to start thinking about it so before we get there. that's going to be huge. You can even imagine like trying to climb up Starship. Again, Starship 100 feet high, elevator, ladder. Are we bringing dust on that? And then we got to bring it inside and we're going to get Starship all dusty. All that stuff's super important. But also the vehicles that are going to be operating in the regolith, right? Like not just for our habitat and our comfort and our survival, but like hopefully we don't have binding of mechanisms and things of that nature. I know we talked about it on LTV with one of the contractors. A lot of cool, sophisticated mechanisms, but one of the questions I asked right out the gate is like, hey, how are you dust mitigating this, or how are you testing it? Where's that facility that we, are dreaming about to do? So all of those things are important, but training right now, I would say it's not on the front end.
Thank you. Maybe to kind of follow on with this, you talked a little bit about kind of the longer term vision as you're thinking about those later Artemis missions. What do you feel like is some of the most critical technologies that will enable more Earth independent as we move more and more towards operations that are sustained on the moon?
Man, there's a lot of things that I could probably say, but I guess I'll go to the things that I like, which is if we can start utilizing more, AI helpers, right? Because we'll have comm delays, and even down to an AI assistant that helps you remind you what it's like to be human. There's this aspect of like, you're detached, you're just focusing on logistics, you're just focusing on the mission. You can call your family and whatnot, but like maybe just that human voice in the back of your display or your heads up, whatever, to kind of help you stay calm. There's also devices where, we have a certain resonance frequency with the Earth that we may not get on the moon. There's other tools like that I don't typically think about that would be great. But then the bigger ones that are more functional and what we need is, location systems, right? I think it's because we've been so used to that here on Earth as technology has advanced. But I say that because, in our office, we'll take ownership and pride that we can do land navigation, which is important when we're out there by ourselves. But if we really want to have force multipliers, right, other robots working with us, like they're going to need that data, whether it's location from GPS or LiDAR sensors. Sensors are going to be a very big part of being able to stay there and work and be efficient and have multiple, agents working together if we're going to build these structures and whatnot. So that'll be important. And the other thing I'll say, which is one of my biggest, I would say, concerns, is radiation. Where's Jamie at? Yeah, like going to Mars, right? Because the moon is the proving ground for Mars. But like going to Mars and even the Van Allen belts, right? Like we got to figure out how to shield ourselves because we're not going to last very long. So that's going to be a big one. And then, of course, the last would be propulsion. So if we want to be interplanetary, we got to do that. So nuclear propulsion is something I've been thinking about a lot.
Awesome. And we've got one more question, I think, before we'll move on to our next panel to talk about so many things that you set us up for.
Oh, good.
But what's something unexpected from your non-space background that you found especially useful as an astronaut?
Well, it's interesting. I think being a naval architect, you look at, astronauts, you don't see that every day, right? Like, this guy works on ships. What's he doing in space? But naval architecture was the first kind of systems engineering that we ever had. We build the ship's hull. We try to optimize it for drag and all these things for the route. We have machinery. We have electronics. We have weapon systems. I mean, all of that is kind of the systems of systems into one type of approach that we see, or that I see at NASA. And it's funny, right? Because, the ISS has a port and a starboard, right? Like vessels or vehicles and stuff like that. So I didn't appreciate, because again, I would say I'm more of a mechanical engineer by foundation. And then when I was like, oh, I'll do the Coast Guard stuff, I'll do naval architecture, that really opened up my mind to be more of a systems engineer. And I thought that was super valuable because you really have to work with multiple groups of people and subsystems to make complicated things happen. And so, I really take that to heart. I'm really glad I took that path, but it was unexpected, right? I thought, oh, there's no water drag in space. Well, don't think that low in detail, like think high level and some of the principles that may help.
you so much.
Thanks for the questions. Yeah. Thanks, everybody.
Thank you.
Thank you. This was great. All right. Okay, and now I would like to welcome up our Proving Grounds panel. I'm not going to go into this because our APL LSII lead, Wes Furman, is going to give you all the information you need to know about Proving Grounds, and he's going to introduce the panel members as well.
All right, thank you, everybody. And make sure that we've got our online friend, too, who's going to talk about the ESA Proving Grounds that I'm pretty sure Andre was calling out as well. So he set us up exceptionally well for this panel. Andre really did. Let's see if I can get our new clicker working. This one. There we go. So we're going to be talking about Proving Grounds, right? And it's really fun to look at a photo like this and think, this is the beginning of what our return to the moon will look like. And some of you may recognize the rover here from our last spring meeting. But if you squint your eyes a little bit, you could imagine it's something else. It could be the pressurized rover that we were just talking about. You can imagine that maybe there's some other elements there, what you want to do for what you're doing next. And this kind of scene is really it's just the start of it, right? We're heading towards an ecosystem of partners working together to satisfy the objectives of NASA and beyond, right? And all of those elements have to work together seamlessly in an environment where we'll have a really hard time fixing the things that go awry. And so this is not the actual scene that we're here to talk about for Proving Grounds. I'm going to ask you to squint just a little bit harder, just really squint at it. Like, I'm actually close your eyes, and this is what we're going to be talking about. So Proving Grounds are they're where we go to make sure that those things don't go wrong, those system-level considerations that we need to have nailed out. That's what Proving Grounds are about. So we heard yesterday about the engineering challenges and had some discussions about the component-level testing and heard some calls about how some of those combined tests are just not possible at this full scale. So today we're actually going to hear about the flip side, where it's essential to leverage those large-scale integrated testing facilities, colloquially called Proving Grounds, and further developing those technologies for the lunar ecosystem. So I'm going to introduce all of our panelists and then do my best to keep them to about 5 minutes or so before we get to the Q&A, which I really love. It's been so much fun to do the Q&A. So I'll do the introductions for the panelists now. Let's see. All right, hopefully this will go. Click. All right, great. This is our panel. We're going to start over here with Nick Downs.
Where'd you get that picture?
That picture? That's from your LinkedIn, right? I think it might be the one we use on our site, too. So Nick Downs is a principal scientist in the geoscience department at the Nevada National Security. It's not working. I'll just point. At the Nevada National Security Site, NNSS, and he's an expert in subsurface characterization and 3D geomodeling. He also supports multiple non-proliferation and nuclear monitoring projects. Thank you. He's the co-founder of the Nevada Space Proving Grounds program at NNSS, which I'm expecting he's going to tell us a little more about. Prior to NNSS, he worked for a decade in oil and gas, exploring for and developing hundreds of deep drilling projects across the United States. He received his MS in geology from UNLV and his BS in geology from Duke University. Next slide. All right, next we've got Dan Hendrickson. Dan Hendrickson is the Vice President of Business Development for Astrobotic, a lunar logistics company based in Pittsburgh, Pennsylvania. Many of you know Astrobotic well from our last fall meeting. So Nevada beware, we're going to ask you to come back and do more things again and again. Dan leads the company's lunar and space robotic sales efforts across the company. And prior to Astrobotic, Dan served as Director of Civil and Commercial Space Systems at the Aerospace Industries Association. All right, this is actually working. So we've got Jürgen Schultz. Jürgen's background is in human spaceflight and systems engineering. He's online, and he works at ESA, where he's responsible for the development and utilization of the Luna analog facility at the European Astronaut Center in Cologne. Jürgen studied aerospace engineering at University of Stuttgart and University of Sydney, Australia. He earned a PhD from University of Stuttgart for his research on conceptual architectures for lunar exploration and on tools for lunar surface infrastructure design and performance assessment. He also lectures at University of Stuttgart and at the Space Tech program of TU Graz. And very LSIC-like, he's engaged with public outreach about the fascination of human spaceflight. He's founder and managing director of ISSabove.eu and organizes yearly space events in Germany for thousands of visitors. So fantastic. And let's see, we've got Terry now. All right. Dr. Terry Fong is the chief roboticist at NASA Ames Research Center and the deputy rover manager for Viper. He was previously the autonomous systems capability lead for STMD and director of NASA Ames Intelligent Robotics Group. Terry's led development of many robotics programs, including Astrobee, Smart Spheres, Robonaut 2, Humanoid Robot, and he's a very prolific author of more than 175 papers in science and robotics. He received his BS and MS in aeronautics and astronautics from MIT and PhD in robotics from CMU. All right, so now we can go on and hear about all of their Proving Grounds panels, see a little bit more about them. Go on to the next slide. And panelists, next slide again. You're going to have to motion for over there when you want to see the next slide. Great.
Can you guys hear me okay? Okay, great. Yeah, morning everybody. Hopefully everybody had their coffee this morning. Early morning in Vegas just hits a little different sometimes, especially after that great reception last night. So while I've got the mic, just want to say thanks to the LSIC team, Jamie, Anna, and everybody else, and obviously thanks to the UNLV team who have put together a tremendous conference for us. So I'm Nick Downs, geologist at the Nevada National Security Site, or the site, as everybody likes to say. NNSS is kind of a mouthful there. I help run our Nevada Space Proving Grounds program out at the site, which for those of you all who are coming on the tour tomorrow, you'll see most of our test beds, not all of them, but most of them. And we very much look forward to sharing these test beds with you all in the flesh tomorrow. Let's go to the next slide here, Jamie. Okay, so I assume that some of y'all have probably been out to the site before, but most of you have not. It's located about 60 miles northwest of Vegas, so out in the desert. It's surrounded by federally owned land, and so it's a pretty remote, pretty large test bed. We are a DOE-owned facility, Department of Energy-owned facility, surrounded by Air Force land primarily. And so the history of the site, as most of y'all are aware, is that we were the primary nuclear testing ground during the Cold War. So out at the site, we set off 928 nuclear weapons. 100 of those were atmospheric, so picture kind of your classic mushroom cloud, some of which you could actually see the mushroom cloud from downtown Vegas, if you can believe that. The rest of them were underground, so over 800 nuclear tests underground in tunnels and in vertical shafts. And for the shots that were executed in vertical shafts, they left behind a litany of large craters. You can see that in some of the imagery below, down at the bottom of the screen. We've got hundreds of large craters that are several hundred meters across. And you guys will, who are coming on the tour, will get to go inside one of these tomorrow and stand on the edge of our largest crater, Sedan. So the site's about 1,300 square miles. It's larger than Rhode Island, and so I'm advocating that we should get at least one vote in the Electoral College. So if anybody thinks that's a good idea, let me know. We're obviously highly secure. The badging requirements are quite onerous, so thank you for all the tour goers for abiding by those requirements. There are a couple other interesting facts, such as we have special use airspace by the FAA. We can basically do whatever we want with the airspace as long as the Air Force isn't flying anything too interesting over us. And most pertinent to LSIC, we were an important training ground for Apollo. So every Apollo astronaut who stepped foot on the moon first came out to the NNSS, the site, and trained in our craters. And there are a couple images down there at the bottom. On the left there's the Apollo 17 crew in their buggy up on Buckboard Mesa. On the right, you can see them standing with their trainers in the Schooner Crater ejecta field, which is really a spectacular place. We won't go there tomorrow. The buses can't quite make it. But suffice it to say, all of the Apollo guys trained out here. And it made enough of an impact on the Apollo astronauts that they actually mentioned it while they were on lunar EVA. Both the Apollo 16 and 17 crew specifically mentioned sites out here at the site that informed their geologic reasoning and informed their geologic sampling while they were on lunar EVA. And so that's something that obviously we're proud of and privileged to have supported back in the day. But one of the other things that we're really excited about is how we're turning the page from Apollo, kind of this historic program, to a living program with Artemis. So let's go to the next slide here. And that's basically the point of NSPG, the Nevada Space Proving Grounds. We've got all of these like old handwritten notes from the Apollo team on what they did where and when they did it and what their training objectives were. But those are largely incomplete. Both our partners at JSC, at NASA, and our archivists have gone through to try and find as many of these historical documents as possible, but I think we've all been left wanting. And so although that's a little frustrating, it's also an opportunity for us to revisit some of these training assumptions and to integrate new technology into how we're training the next crew of astronauts like Andre and how we're developing new tools to support our astronauts. So we had a return of NASA to the site about a year and a half ago for the Jet 4 exercise. You can see down in the bottom left there, that's one of our JSC, not crew members, one of our JSC engineers wearing that same Atlas suit that Andre was wearing earlier, pushing the tool cart at night in front of that large tower. That's called Ice Cap Tower. This is a nuclear emplacement tower that was left behind when nuclear testing stopped in 1992. And it just so happens, fortuitously, to be the same dimensions as HLS Starship. It's 50 meters tall, about 9 meters diameter. And so, don't have to tell you guys, it's not common to find a 50-meter tall desert, or 50-meter tall tower out in the middle of the desert surrounded by hundreds of large craters. And so when we informed our JSC friends that we have this thing out in the desert, they booked their tickets like the next week and came out. And so suffice it to say, I'll kind of wrap it up here. But we're actively working with NASA on an ongoing JET exercise right now. Today is the first day of the JET 7 exercise. So for y'all coming out on the tours tomorrow, you'll see NASA executing real time around Ice Cap Tower, crawling in and out of these craters. We'll be executing some navigation, communication, and science objectives. So it's a pretty ambitious program, but we'll be executing through the weekend and into next week with them. And so very much looking forward to talking to more of you guys in person on the tour. Please hit us up with any questions. We're not going to tell you where we bury the aliens or where we stage the moon landing, but look around and some of those scenes might look a little familiar. But at this point, I'll turn it over to Dan. Thanks, Jerome.
Great, good morning. Thanks very much. It's great to be here. My name is Dan Hendrickson. I'm with Astrobotic, an aerospace company based in Pittsburgh, Pennsylvania, as well as Mojave, California. And in fact, we'll be speaking a little bit more specifically about the Mojave side in particular when it comes to the proving ground that we've built out in the desert there. So if we could go to the next slide. So Astrobotic was founded back in 2007 with the primary mantra of making space accessible to the world, and we believe that the moon is the best place to start. And so it's with that in mind that we are developing a whole host of space robotic capabilities that we think will underpin our future in a sustained presence on the moon and beyond. And in particular, we're focusing on space transportation, mobility, and power services for customers all around the world. And this picture, I think, really kind of sums up what we're really trying to do. A sustained electrified presence on the moon and making that as a service that's available for everyone. There's a lot of steps to get from here to there. And so we are focused very intently on developing all of those steps. In particular, if you go to the next slide, this kind of sums up all of our products and services that really represent those steps. You can think of this as kind of a cradle-to-grave representation of all of the services that we're offering to our customers to be able to access the moon. But that doesn't mean just actually getting there. It means also preparing and developing payloads and capabilities to enable getting to the surface in the first place, and then to be able to make the best use of your time once you're there. So on the far left, you can see that we have rockets. These are vertical takeoff, vertical landing vehicles. They come from the legacy Maston Space Systems company, which we acquired about 2 years ago. And one of the really exciting things that we were most motivated by in bringing Maston on board into Astrobotic was to continue and to grow those vertical takeoff, vertical landing capabilities, because we think that really represents an industry-unique capability to prepare for the lunar surface and to really that last few hundred meters going down to the surface. And so we have focused on developing not just a cadence of flights, but also upgrading the vehicles that we're going to be doing those VTVL flights in the future, as well as building out the lunar surface proving ground, which we'll talk about here in a moment. So as we provide that on-ramp for customers and for stakeholders to be able to prepare for the moon with these VTVLs, we also provide uncrewed robotic transportation on our landers. Our rovers provide sort of the last meter of transportation to make the most use as much as possible on the surface once you actually get there, since it is so hard to get there in the first place. And then power to be able to provide sustained presence to not only survive the lunar night, but then also to thrive during the lunar day. If you go to the next slide, we'll talk a little bit more specifically about Zodiac. So this is the vertical takeoff, vertical landing vehicle that is in service today. It flies pretty much every week now in the Mojave Desert out at the Mojave Air and Spaceport where we're based. This vehicle is providing the capability for customers to have in the upper top portion you see on the right of the vehicle about 35 plus kilograms of capacity. We provide a precision landing capability for doing the final approach to a planetary surface, in particular the moon. And so this capability is all the way down to 3 centimeters of precision. That 3 centimeters is actually really just the final bounce that the vehicle makes once it touches down. So it is very highly precise. We offer closed loop testing for folks. So this allows folks to actually take control of Zodiac with particular GNC payloads. The vehicle and the program has been set up to provide guardrails. So if you go outside the nominal trajectory, the vehicle takes back over. So it does allow for a lot of really meaningful testing. And the vehicle is powered by a LOX alcohol engine, the Scimitar engine. This allows us to fly regularly and often. So as I mentioned, we're flying every week now. We've done 170 successful flights with Zodiac, and we're booked now well into next year. Still have more opportunities to fly and still can carry additional payloads in 2025. But as you can see with the different stakeholders and customers on the slide, many folks are taking advantage of this opportunity, which we think, again, is industry unique. If you go to the next slide, this shows the range of different trajectories that Zodiac flies. Does about 500 meters in max altitude, can go about 300 meters downrange. So really this is, again, the last few hundred meters of testing of getting down to the surface. And so it really provides, again, a unique testing environment. And we're pairing that now with the lunar surface proving ground, which on the next slide here, we'll have some information on. Or sorry, that'll come in just a moment. But just to highlight with Zodiac, if we go to the next slide, the campaign of testing that we provide for our payloads starts with integration. We provide a checkout, we do 2 tether tests, and then we actually do the free flight. So all of this happens roughly within about a week. So it's a very fast turnaround, but that's great because that provides our stakeholders an opportunity to get results quickly and to fly again rapidly, which is not a frequent hallmark of flight programs necessarily across the whole industry. So we're very excited to be able to provide this kind of cadence. think on the next slide, we actually have the lunar surface proving ground. So the image that you see here on the left, this is the actual proving ground on the bottom. This vehicle, as I mentioned, Zodiac, which flies over the lunar surface proving ground, this is what really provides that final trajectory to do the testing. And apologize, the screen here just blanked out, so that's why I'm turning around so I can align. But we provide, with the proving ground, the features of craters and ridges that align with the actual site at the South Pole that our Griffin mission is going to be flying next year. So that mission is going to be flying for a landing site near Nobile Crater. And so we modeled the lunar surface proving ground to match that landing site to provide a very South Pole relevant location for folks to do testing. So this proving ground provides the opportunity for flying on Zodiac to come down, and you can actually do some custom lighting conditions at the proving ground to be able to simulate what we think it'll look like. There's been some great presentations by folks in the past, by folks like Jake Bleacher, who pointed out that the lighting conditions are going to be so unique and so different than what we had seen during Apollo at the South Pole. And so this proving ground allows us the capability to be able to provide some of those extreme lighting conditions to understand what it'll actually look like. And so you can do things like terrain relative navigation testing, hazard detection, LiDAR testing. We can have obstructions, again, matching what we think the actual South Pole will have and what it'll look like. We do this with a unique stucco concrete mixture at the proving ground. Unfortunately, we're not able to use actual simulant because we are actually out in the desert, so it would literally blow away. So that because it is an outdoor proving site, we do have that challenge of not being able to use true simulant, but it is optically accurate. And we have actually built and modeled our proving ground using our LunaRay software, which was designed originally to do digital elevation maps for our terrain relative navigation sensors on our landers. So we needed really highly accurate lighting condition maps in general of the landing sites that our landers were going to be going to. We then used that tool to then inform what the actual lunar surface proving ground looks like out in the Mojave Desert. If you go to the next slide, I think there's a larger image here of the proving ground actually at night. So again, we can do these really unique lighting conditions. We can have lighting that's actually much closer to the ground and actually even make it more dramatically like what we'll see at the South Pole to really get an understanding. And in general, I'll just highlight, maybe and close by pointing out that this is a proving ground that's available to you now. There's flight opportunities calls that NASA STMD hosts on a regular basis. Through that program, you can get funded flights on Zodiac with the lunar surface proving ground. So we're open for business. This is a capability that we will help you to propose to. We've got a lot of great information that we offer, and we help PIs put things together, put proposals together. So this is your lunar surface proving ground, and we're really happy to work with folks to help get use and get ready for the moon with it. Thanks very much.
Okay.
This is our online friend from ESA,
Yes.
Jürgen. Can you come off mute?
Can you hear me well? Does that work?
Yes, we do. We hear you.
Then I say thanks a lot for the opportunity to participate, also from remote. Even though it's late evening here, I'm happy to join you in the early morning in California or in Nevada. I want to talk about what we have established over the last year, basically, with some planning ahead of that, and that is the ESA and DLR jointly developed Lunar Analog Facility. And I think it was a great introduction that we had this morning by Andre and now by Nick and Dan that mentioned a lot of the challenges that we have in preparing for the moon. And when we started discussing that at ESA and together with our colleagues in DLR, we figured that we needed something that closes a bit of the gap between the actual field testing that is typically involved with a lot of logistics efforts, with a lot of uncertainties in terms of the environmental conditions that you will have, and the system scale testing that's done all over the world in different labs and spaces. So we decided we need to build our own analog facility, a facility that's large enough to do human scale testing, infrastructure element testing and training, but that also is fully indoors, fully enclosed, environmentally controlled, 24/7 available. And that led us to developing what we call the Luna Analog Facility. And you see a picture here on the starting slide already. That's the hall from the outside. The facility has just been inaugurated in September this year. So about 2 months ago, we've basically started business. We've started constructing the facility about a year ago in summer 23, and are now ready to have our first initial activities in the test field. And I will lead you a little bit through what that facility can do, what our ambitions and aims are, and then I'm happy to discuss with all of you about the opportunities later on. So if you can go to the next slide. What the facility really is trying to simulate and work on everything that will eventually happen on the lunar surface, from landing on the surface to leaving the surface without the actual landing and launch aspects of the mission. So what the facility entails is a large building, and that features, if you click once more, a couple of different features. So we have a large Regulus test bed, about 700 square meters of test field, with about 900 tons of Regulus simulant. We actually use true simulant, the EAC-1A simulant that we have characterized at the European Astronaut Center in Cologne, which is a basaltic Mara material, but very close to what we expect or what we know about the lunar surface material, very dusty material. We've actually looked at using the fine-grained material so that we are representative of the lunar surface. That material is locally sourced here in Germany, but we also have an additional dust chamber, a smaller room that we actually have with a dedicated Highland simulant that we've sourced out of Greenland, that has a different look and feel, and that we can also use to simulate impact of dust on lunar surface, on materials, on seals, on different mechanics that can go to the lunar surface. So that Regulus yard is already in place. You see a live picture here, and you can also estimate a little bit the size. It's about 21 by 34 meters. And we've also brought in a couple of geologically relevant samples because we want this to be relevant both in terms of training astronauts, in terms of understanding geological context possibly, and or simulating that, but also in terms of testing instruments, in terms of testing sampling from rocks by astronauts or by robotic systems. So we've brought in rock material from different regions where the astronauts train, particularly in Europe, from the Etna volcano in Italy, from the Nördlinger Ries crater, the impact crater in Germany, but also from the Lofoten in Norway. This is the places that our astronauts go for geology training. And we can now prepare that also here in the facility, and use the same tools and tool sets in order to validate actual surface activity. We have the facility is also large enough to actually host different mock-ups in human infrastructure size. What you see here in the picture on the upper right is actually a one-to-one sized mock-up of the Argonaut lander of ESA. This is supposed to bring cargo to the lunar surface for the Artemis missions. And we can test all the unloading and interfacing with such kind of a lander in the facility eventually. We have already a full ground segment set up, and what you see on the lower left-hand picture is actually a visitor room that we've set up in order to also do outreach from the facility. But the important part that I want to highlight is that the whole facility is really built into the ISS ground station network. So it's directly linked to EAC, to the DLR, Microgravity User Support Center and the German Space Operations Center in Munich, and technically then to all ISS operations centers around the world, which makes it a very high quality simulation in the facility with respect to actual operations. And I think that's the main focus that we have in terms of understanding ConOps for lunar surface activities. We're using the EVA suits that we've seen already this morning, the Atlas XCon suits. We have 2 of them already here and tested them already a couple of times in the field with our astronauts. And while we don't only want to do activity on the lunar surface in terms of EVA activity, we also want to simulate actual IVA activity on the surface and be able to eventually run full mission simulations, which is why we are also establishing moon-based elements around the facility. And we are currently installing what we call FlexHab, a habitat element for 4 crew up to 2 weeks. And that will allow us to simulate full Artemis mission context, and that will be fully installed in March next year. If you go to the next slide, those are all the elements that are already available today. And we've just finished over the last 3 days, our first scientific campaign in Luna, which was a geophones seismic activity measurement campaign that has been carried out in the test field. We'll have another campaign next week and in the first week of December. And we are currently targeting initial EVA activity in early next year. The other features that really make us stand out eventually, besides the operations environment and the dusty test field, is also the illumination conditions that have been mentioned a couple of times now already. We can, since we are indoors, we can actually simulate all the illumination conditions at the lunar South Pole specifically, and we are installing a sun simulator for that. And the other feature is reduced gravity. Because we're indoors, we're actually working on developing a gravity offloading system that will enable multiple assets, so that can be astronauts, but also robotic assets, to actually be offloaded with 5/6 of their weight, so that they can have surface interaction at 1/6G. And that system is currently being developed for a prototype in 25 and will be fully installed and rolled out in the hall in summer 26. And that will be a unique environment then to test for all surface activities. Also, there's elements like a ramp system for dedicated slope activities. We are looking at different sized rovers. We are integrating extended reality and virtual reality aspects into the training, but also into the actual activity in the hall, and looking at aspects like experimental, exploration medical systems with all the capabilities that we have in DLR and ESA already on the site. So if you go to the next slide, I just want to give you a quick impression of what that looks like today. This is a picture that was taken during the inauguration in September. So here we already have 2 astronauts in the XCON suits with a tool cart that was developed also at EAC, looking at some sampling activity and demonstrating a bit how those kind of EVAs could look like, also showing a bit the illumination conditions that we can create, even though this has not been the final sun simulator that had been installed at the time. But I think it's already very moon-like, and I'm really looking forward to testing more. If you go to the next slide, I just want to say, and you click twice, a few final words on how we want to use the facility. The thing is, it's really, we are providing a facility. So we have our own ideas for using it, but it lives and really comes to life from the ideas that others bring. And we want to make this community available for the community. So one aspect is obviously for NASA Artemis to understand how we can do EVA simulation and training, how we can do mission simulations and surface infrastructure deployment and support in terms of the actual technology development. But for the lunar community, I think it offers also a lot of opportunities in terms of technology development, operations, science operations integration, and even mission simulations on a robotic scale. So that we are really looking forward to, and I'll leave it at that for this morning. We welcome you all to Luna eventually. If you want to start understanding what to test, please feel free to contact me. If you go to the next slide, there's also a website listed where we have regular news about Luna and where you can find email contact to contact us, and we can bring you, get you in all the information about applying for potential utilization of the facility. While we're, I must admit, at the moment still sorting out a little bit of the legal framework that's relevant for that in terms of third-party use. But our plan is that we can start that early next year.
Go to Terry. Next slide.
All right, good morning, everybody. Is there another mic that's on? Okay. Okay. I'm just being very loud today. As you can tell from the title slide here, I'm going to be talking about something completely different, which is a software-based proving ground, a digital proving ground. But before I begin, I'd actually like to point out a couple things. One is this presentation, plus there's 2 more coming in the next panel, are intended to give you a small snapshot of some of the technology development and technology capabilities that have been created for the Viper mission. These technologies are things that NASA has spent a tremendous amount of effort, time, and of course dollars over the past several years developing. And regardless of whether or not Viper flies anytime soon, and of course I think everyone in this room probably would agree that flying it sooner is better than never flying it, I do want to point out that these technologies are available for reuse, and it's the full intent of the Viper team to try to encourage and support the adaptation, retargeting, and reuse of these technologies. So if you see anything here or in the next couple of presentations that you're interested in, or if you'd like to learn more about Viper technologies, please find me or Bill Bluthman or Matt Deans and talk with us. We're here to help you better understand what Viper has developed and help you make use of this. The second point is I want to point out, I want to acknowledge, and I want to very publicly thank the Space Technology Mission Directorate. Many of the technologies in Viper got their start with STMD support. A lot of the work that's been done on Viper would not have been possible except for the support of the Game Changing Development Program, the SBI or STTR programs, and tipping points. A lot of the things that you see here, STMD doesn't get enough credit for. It's not just an SMD mission. The base of technology got its start with STMD. Now, with that said, let me tell you about Digital Proving Grounds. Could we click the... Great. So Viper, as you all know, is a lunar polar mission. It was intended to operate for about 100 days, prospecting for subsurface water ice, having to deal with very difficult constraints, such as the fact that the shadow fronts, these are the long cast shadows, the illumination fronts, move about the same average speed as the rover, which means you have to deal with the fact that the rover has a very dynamic environment. You have to basically chase the sun or run away from the shadows. You have to stop and pause and wait for the conditions to be right to continue. That poses lots of challenges for us in terms of development, testing, and training. All kinds of questions about how do we recreate in very large scale under accurate conditions in terms of sun elevation and lighting response at lunar surface appearance in order to do development, validation of requirements and ultimately training. There are other questions too in terms of how do you do adequate terrain relative navigation. As Dan was pointing out, this is a big challenge for these kind of systems that we build today that rely heavily on cameras and computer vision. I will say that it's quite different if you're trying to build a terrain relative nav system where you're primarily pointing downwards in the case of landers, where you may be able to limit the extent. Versus rovers, which look out over the horizon and need to see really far away for some features. That requires you to actually create training area or testing grounds that are very large extent. There are other reasons too that if you're trying to really develop how a high ops cadence interactive science mission works, you need to be able to conduct high fidelity, scientifically plausible, highly accurate simulations. And you need to be able to do this in a variety of areas. In particular, you need to be able to recreate parts of the moon that your mission is targeting so that your development and your training is accurate for that. And then, of course, other things too. In terms of trying to support agile development, you need something you can use continuously, not just going out and doing a few-day test or a few-week test, but every single day, every single hour. So next slide. So I told you about the why. I'm going to tell you now a bit about the how that Viper created a digital proving ground. And if you could click 3 more times. Oh, okay. Well, they're all kind of grayed out here. I'd intend to be clicking these myself, but I'm going to tell you very quickly over the next 3 or 4 minutes here about 4 pillars that feed into the software simulation that Viper uses and has used for several years now. I will say that a lot of people in this community, when they talk about simulators, are really focused on the rendering engine. They'll tell you, oh, this uses OpenGL, or it's based on Unity, or in our case, we use Gazebo. That's a very important part, but it's not the most important part. In fact, what's missing, what a lot of people will tell you about, are all the other things that feed into that. One thing that's incredibly important, of course, is the quality of the lighting. You need to have a very good understanding of the lighting conditions, and that's not just solar illumination. There's earth shine, there's moonshine, there's the reflections and the effects that you see from the opposition effect. A second part is that it's not sufficient just to use an out-of-the-box camera model. You actually want camera models that are reflective of the systems that you use for flight. So Viper, for example, has done extensive amounts of testing characterizations of cameras and used those to create equally accurate camera models that are used as part of the simulation. A third area for rovers, of course, is we worry about the wheel-soil, the mobility-soil interaction. So understanding how vehicles perform as they drive, what sort of slip, embedding, entrapment do they see is very important. And in our case here, we spent quite a bit of time using our physical testing with our physical test beds to help calibrate the models we use in simulation. And the fourth area has to do with the quality of the terrain models that you use. Now, of course, we all work with digital elevation models. The question is, how do you go beyond those models to the kinds of things that are necessary for the sort of testing, development, and training purposes that I talked about just a minute ago? Next slide. So first off, very quick overview. If you're interested in more details, come see me in the breakout this afternoon. In the area of high-quality lunar lighting, we've been fortunate for the past several years at NASA Ames to take advantage of a very creatively named lab called the Lunar Lab. It's a large sandbox with many tons of LHS-1 simulant, and we have a high-fidelity sun simulator that we use for actually acquiring detailed knowledge of appearance on the lunar surface under a variety of different conditions when you're looking down sun, up sun, cross sun. If you could click the next slide. This is a video just giving you a sense of that. It's a fairly large sandbox, 4 by 19 meters, which means, of course, you can only do scaled calibration and testing here. We do recreate the lunar surface using size frequency distributions of craters and rocks, scaled down, and then the sun simulator, of course, is scaled down as well. But this does allow us to have very, very high fidelity, accurate, controlled testing and characterization of lighting conditions. Next slide. We use this, as I said before, to help feed into improving the way that we create camera models for our software simulation. So on the top row here, you'll see data that was acquired. These are images captured with engineering cameras that Viper has used. On the bottom row are the simulated camera images that we produce with our software simulator. And you can see very good correspondence in terms of exposure here. Next slide. We also take a look at other things such as lens flare and other stray light artifacts. Next slide. And even down to the level of worrying about imager effects, so fixed pattern noise, flat field effects, and looking at depth of field. These are the kinds of things that if you really focus on high accuracy, high quality calibration between test data and simulation data, makes the simulation much better. Next slide. I mentioned also that we care a lot about slip modeling. On the bottom left there is a picture from the Slope Lab facility at NASA Glenn. We have done a tremendous amount, hundreds of hours of testing with our engineering mobility platform for Viper. You can see a video of that playing in the upper right corner. Driving up and down slopes, driving over obstacles such as craters, rocks, rocks inside craters, on slopes, on the GRC-1 simulant. And we've used that to help develop and tune a calibrated vehicle model in terms of slip that we feed into the simulation. This allows us, when we use the simulation, to recreate in a way that we believe is highly reliable in terms of the way the vehicle performs as it's driving across terrain. Next slide. The last area is in terms of high-resolution terrain models. Of course, we all rely heavily on DEMs, in particular DEMs, based on data that comes from LRO. Most of the data sets that I see people use are in the 3 to 5 meter per pixel range. This is based on LOLA data or the use of wide baseline stereo. In our case, we've been fortunate enough for the past 10 years to have a tool at Ames called the Ames Stereo Pipeline, which during Viper we really enhanced to make use of shape from shading techniques in order to generate 1 meter per pixel DEMs. So these are actual DEMs at 1 meter per pixel of the lunar surface based on LRO data. If you could advance this. We've augmented that with a synthetic terrain set of tools to get to much higher resolutions, but still scientifically plausible. So Viper did a lot of internal analysis, which has not yet been published. We hope to do this within the next several months, in particular in terms of rock size frequency distribution and small craters. This is like the 5 to 20 meter diameter class analysis of craters that allow us to then take that information and create synthetically scientifically plausible terrain. And in this case here, this is a 4 centimeter per pixel DEM that we use as part of our simulation. Next slide. And Wes is telling me to wrap up here, so just a couple things here. This is what it looks like when you put it all together. This is the Viper RSim, or rover simulator. We're not very creative with names here. You can see very, very high quality illumination modeling, very high quality appearance modeling here. We've used this for software development. We are right now finishing up requirements V&V with the simulator as part of our overall V&V approach, and it has fed into the several thousands of hours that we've done in terms of mission ops training. And last 2 slides, I think, if you could click. In terms of mission operations training, this is the Multi-Mission Operations Center, NASA Ames, if you could advance here. This is the rover, one of the rover interfaces that we use to drive. And the very last slide, if you could just click that, okay, back up 1 slide. You'll see here we have on the left, this is the rover driving interface here. On the top right here, I guess the video's not playing, but it's the RSIM simulator. We use this together, and I will say that this use of RSIM has been absolutely essential, really critical for our ability to develop Viper over the past several years. But hopefully I've convinced you that software proving grounds have a place, and they're very complementary to the physical ones we've talked about. Wes.
Thank you, Terry, so much. I mean, so there's a fantastic diversity. Thank you. Fantastic diversity of proving grounds approaches and the things that you'll be able to accomplish with them. And one of the first questions I was going to ask all of you is, what niche did you try to fill with the facilities? But actually, looking at the questions as they're coming in, they're already kind of getting at those questions already. So I'm just going to go straight to the questions that are coming from you all, add more with the QR code through Slido, and we'll keep going in our conversation. So I'm going to circle back around to Nick. Some of the questions that we're getting for you are, what are some of the unique infrastructure elements that you have that could translate into additional sorts of testing? So specifically, is some of the tunneling infrastructure translatable into lava tube exploration, training, other sorts of elements that you could use at your facility?
Yeah, it's a fair question. Unfortunately, we won't be able to take y'all underground tomorrow, but on future tours, that is possible. There's a lot of legacy infrastructure out at our site that just simply doesn't exist elsewhere in the world. And some of that can be tailored to lunar analog testing or Martian analog testing, like in the case of lava tubes. Yeah. I guess to kind of twist the question, it's really interesting, I think, to see how just over the past couple years, the available proving grounds have both proliferated and diversified. Yeah. It really does strike me today, listening to Astrobotic and to the Luna program and others, that there are a lot of niches that are currently being satisfied. I'm almost struggling to think of what other niche is out there that is not currently satisfied. Yeah. Whether it's benchtop scale testing, under vacuum, under cryo temperatures, like Dr. Susante's lab up at Michigan Tech, or sandbox scale testing, or tennis court scale testing, or kilometer scale testing, which is really kind of our expertise. There's something for everybody, I think, at this point. But I'd like to hear the opinions of my other panelists to see if you agree or disagree if the spectrum of available niches is currently satisfied or dissatisfied.
Oh, that's great. And I also want to add the specific questions for each of them, because our panelists are asking does your niche fill? Is this then part of your niche? Go ahead, Terry.
I was going to say that I think every single one of these proving grounds has areas where they have strengths, and there are obviously limitations for all of them. There's no single proving ground that does everything, just like there's no single analog site for any kind of testing that does everything. And I think it's really important for us as a community to better understand, okay, where are the intersections? Where can we carry out tests? Just like the panel yesterday where someone said, well, when can you carry out multiple things at the same time during testing? The same is true about the use of proving grounds.
So Dan, I'm coming to you. For your facility, is the Astrobotic Proving Ground in Mojave available to non-flight science testing efforts, the unique lighting, and then also for PSI? There's a couple questions that are getting at some of the unique capabilities that might be possible with yours. So I don't know if you can answer some of that. Yeah.
Yes, absolutely. We always imagined that this proving ground could be available for other types of testing. It doesn't have to be Zodiac. Now, it is certainly optimized from an optical perspective for a descent that's coming in, and you're having that last few hundred meters of trajectory coming down under a powered descent. But we're absolutely open to using it for other use cases. I think Terry was pointing out, it is such a unique navigation problem that's different when you're actually on the surface and you're looking out. I don't know that we've specifically looked yet at whether this sort of proving ground would help with that kind of testing in the future, but we would absolutely love to explore that. PSI is a little bit harder just because of the nature of the the actual proving ground material that we're using, because it's not really going to be it's not meant to blow away. We environmentally can't really do that at the Zodiac test range. However, we do have some other test stands that we've developed specifically for PSI. And so we've got one test stand in particular that has some gravity offloading to actually do some test runs of that capability, but it's just a different scale. I mean, it's more of a test stand rather than a full, 100 meter by 100 meter proving ground.
Yeah. I've got a question for Jürgen now, so hopefully we can get him on our screen too. There's a couple questions about your Luna facility relating to your simulants and some of the activities that might be planned for that. So there's a couple that are about the density profiles of the Regulus simulant that you've got, if you've done any of the sintering or have some plans for how you might do that in your facility. And then finally, there's another question for you about some of your gravity offloading system. So how do you manage gravity offloading when you've got multiple systems coming together? So maybe you can talk about some of those aspects of your proving ground, of Luna.
Yes, of course, I'd be happy to. So let's start a bit with the Regulus and the simulant, the bulk density profile. So actually, we had a lot of discussion before we actually started procuring the simulant and filling the facility and understanding how we actually handle that. And we have the largest part of the facility filled at about 60 centimeters depth, which is sufficient to have a proper interaction with the Regulus rather than the actual concrete test bed. But then we also have the deep floor area that provides up to 3 meters of depth that will allow us to do also a lot of the sampling and subsurface testing and technology developments that we want to do. We've discussed a lot with scientists on whether we should look at specified density profiles in the test field, and eventually actually decided against it, because the common understanding was that there is a natural how do you say that, compensation of the material that happens when it's filled in, and also when it's walked over, when we do activity in the test field, that is probably representative to some extent what will happen, what has happened on the moon, in terms of natural compaction of the material. Also the Apollo astronauts didn't like sink in anywhere on the lunar surface, or there was not a problem of general density profiles, is what our feeling was. So we discussed for a while whether we want to install some means of loosening up the Regulus in terms of reshaping it after activity, but we decided against it. We have some means of reshaping the Regulus in terms of manual reshaping, in terms of moving the Regulus around, and that will naturally loosen it up. But then we do no artificial compaction, but we just leave it to the natural processes. When it comes to sintering, we actually do look a lot at sintering. We have different activities ongoing. There's DLR institutes, the Institute of Material Physics in Space, currently involved in assessing laser sintering with the Regulus material that we have. That's currently being done in the lab, but we are planning to move some of that activity potentially into the hall. The same thing we're doing with microwave sintering at EAC, and there also we're developing a mobile system that we can roll out in the hall. It has not been done in the hall yet. We're planning to do that eventually. But also there, I mean, we have to see what scale of testing we actually want to do in the facility, because in the end, we don't want to sinter our whole test field. At some place, we still want to have it pristine. So it's at the moment that's more done in the lab than in the test field, but eventually we want to look at mobile systems that can go on rovers and understand how they would operate on the surface eventually. And then on the gravity offloading system, it's actually a very unique system that we're looking at that allows multiple asset offloading at the same time, because it's based on let's say vehicle-based system on the ceiling. The individual elements can move throughout the hall and throughout the full hall and at their own leisure. What it does not offload is obviously the simulant itself, the surface. And that, I think, was one of the questions that I read, is that while the system, the astronaut or the robotic system itself is only touching basically the Regulus at 1.6G, the Regulus itself doesn't change in terms of behavior to behave like it would on the moon. And that's true, and we cannot do that. We're actually working with some scientists on developing potentially a simulant that could do that without needing to offload it, but that could simulate that behavior on the 16G. But that's research in progress at the moment. And we also cannot offload individual, let's say, limbs or smaller scale assets. So also that is something that we're looking into, whether that can be done at some point in time with extended gravity offloading system or with external exoskeleton systems or things like that. But at the moment, we are mostly focusing on the mobility aspect of walking and driving on the surface. And for that, the gravity offloading system is perfectly fine.
Thank you so much. And to circle around now to Terry, there's a bunch of questions that I think all boil down to access. Is there an API code-based way to access RSIM? You know, how do you bring your digital proving grounds to meet some of these other proving grounds so you can do kind of before you arrive at one of these? What can you do with your digital proving grounds? So maybe you can address some of that access.
Yeah, and in terms of access or maybe more broadly reuse of some of the things that I talked about, Viper at the moment is in an officially a closeout and prepare for partnership phase. Part of that has to do with how do we package, document, and release some of the technology that we have developed over the past several years. In the areas that I talked about here, there are some things that you could get right away. For example, the AIM stereo pipeline is open source, including the shape from shading updates that we've made to generate 1 meter per pixel DEMs. The synthetic terrain toolset is in process of being packaged up to be released. The overall fully integrated thing is a bit more complicated because it is so closely coupled with Viper right now in terms of like vehicle kinematics and ties to our overall flight software. But it's part of our process right now to try to figure out what can we get done over the next few months to push out, and feedback from the community would be incredibly helpful to help us prioritize those things.
Fantastic. That's perfect. Now, I'm going to come back around and go back to Nick, and we'll go through again. One of the questions that we have for all of the panelists is, this is an area of lots of rapid changes, and one of the highest rated question right now is how can each panelist discuss how your proving ground is adaptable, specific proving ground changes you might be able to make that would accommodate different community needs as activity increases, as some of these things change. So we'll start with Nick and then go down again.
Yeah, sure. Well, speaking about the NSS, the site in particular, this is a place of high hazard experimentation. That's kind of our bread and butter, and that's really the role that we fill for our national lab partners within NNSA and DOE. And so there's not much out at the site that you can't do. After you've nuked someplace like 900 times, like you can't hurt it too much more, right? Like one way to think about it, perhaps. That having been said, we do take our environmental stewardship very, very seriously at the site, and you'll see a lot of that tomorrow. But when it comes to things like crater modification or devegetation, which is currently something we have not done yet at our test bed, but is something we're endeavoring to do, all of that is possible. It really just boils down to how it's going to be funded, how it's going to be supported, and that's probably kind of a similar answer for other proving grounds around the world. Anything can be done. It's just kind of a question of funding and demand for those changes to be made. But it's a pretty open book for us.
Dan?
Yeah, I think for us, we could absolutely expand. We can add additional sites. There's a lot of room out in the Mojave Desert to work with. So I think we can add additional locations that we could map for other landing site possibilities. I'll also note too, just the VTVL capability itself is also evolving and upgrading. So for instance, we have our Zogdor VTVL that will be the successor for Zodiac. That's going to be able to go higher, it'll go faster. It will also have profiles that will allow us to do 1/6 gravity testing. So there's whole new flight profiles that we're going to be able to take on that we can pair with other additional sites that we can create with the Lunar Surface Proving Ground. So I'd say the ability to pivot to other testing regimes is going to be very much something that we can do rapidly. In fact, the lunar surface proving ground that we just built, I think that was done really in less than a year, from conception of we want to do this to, okay, now we're going to do flight testing with it. So we're, I think, proving that adaptability and flexibility and speed already.
Awesome. And Jürgen, I know yours is still just coming up, but maybe you can tell us how you're sort of planning for this eventuality.
Yes. So the thing is, actually, with Luna, we're not so much targeting of representing a specific site on the moon. It's, I mean, the facility is large enough to actually do human scale testing and infrastructure deployment, but at the same time, it's not large enough to actually properly resemble a full landing site and the range that humans or even robotic assets would actually have on the lunar surface. So as such, but since we have an indoor facility, we can reshape quite a bit. And easily, in terms of reshaping the terrain, in terms of also creating different features of the surface that we want to simulate. Like I've mentioned, the ramp system where we can have individual slopes. It's a 4x8 meter ramp, so it's quite high and can go up to 50-degree slope with regolith on top. So that means that we have a full scale of capability to test going into and out of a crater, both with humans and with robots, and with gravity offloading eventually, starting from 26. We have also the deep floor area that we can use to shape artificial crater inside the facility. We have different means of looking at placing targets, placing rocks, placing shadow creating obstacles that provide the lighting and challenging conditions for elements that move around the surface. So that can easily be done. But then, as I said, we're not at this point in time recreating a specific site on the surface.
I'd say the Viper RSIM at the moment, of course, is targeted to support Viper, which means that the environment that we model is the Viper's target landing and operational area near Nobile. It obviously could be easily adapted to other places on the moon, but by and large, the simulator right now is focused primarily on supporting robotic surface missions. That's what it's designed for. I think it would take a bit of work if we wanted to make it support human testing. So, for example, thinking about how we would actually render things that would be accurate for human perception. There's also questions about what would we need to do to extend this or maybe enhance it so you could run faster than real time. Software oftentimes would benefit from running faster than real time. Right at the moment, we run just a little bit faster than real time at times. Most of the time, it's just to support real time interactive testing. But I think that's in some sense, that's a technology development question. As I said at the very beginning, Viper benefited from initial STMD support to help develop some of these technologies, including parts of the simulator. And it's gotten to a point where it's very useful for Viper the mission. Going from Viper the mission to other missions will require different technology development and extensions. And maybe that's an area that STMD or industry could prioritize. If you have thoughts about what you need and how to do that, I think it's important to recognize that NASA, just like any other organization, doesn't exist to sustain things indefinitely. So there is no Viper RSIM software team that's magically going to support it for the next 10 years. We can release software now, but somebody's going to have to take it and maintain it, and software, like everything else, rots away. So.
All right, that's good. So I want to finish. I know we're going to a break very soon, but I want to finish with one quick last question, maybe just like a sentence at most from each of you. And it's, what testing are you most excited to conduct at your proving ground? What would be like the test that's like, that is so awesome? So we'll go through again, and Nick, we'll start with you.
Oh gosh, for me, I'm so very much looking forward to having Andre and the rest of the astronaut crew out executing kilometer scale EVAs with lunar terrain vehicles in support. That'll be great.
Awesome. Dan?
I'd say night testing. We have had actual Zodiac flights where there's been absolutely no lighting at all. There's the question of like, can your LiDAR sensors operate with absolutely no lighting? And the pictures and the videos are awesome. I highly recommend look them up. It's beautiful.
Thanks, Dan. Jürgen? If we can get you. Otherwise, Terry, we'll go to you first, and then we'll circle back to Jurgen with his exciting test.
Yeah, Viper and NASA Ames in particular has already started working with a few organizations that are, some of whom are in this room here. I'm really excited to see how what we've developed can be used for other lunar surface vehicles. I'll just leave it at that.
Awesome. Yeah. And Jurgen, last call if you were there.
Yes, sorry, I was a bit slow in unmuting there.
It's all good.
But I mean, the Luna, our ambition for Luna is really that eventually everything and everyone that goes to lunar surface will eventually come also to Luna for testing, for training, and that it can take a place in being a surface proving ground, not only before and in preparation of the mission, but maybe also in during the mission, in troubleshooting, in emergency response activities. All these are things that we're looking at, and this is quite exciting.
Fantastic. And one thing I want to point out, there'll be breakout sessions where we can have more of these discussions. There was a lot of content here, a lot of things that are not going to be finished in the questions here. I know that there's a lot more interest. So please look around for our esteemed panelists to continue the conversation.
All right. Thank you. Let's thank the panel one more time. Okay, as Wes told us, we have a break, but before you run off, I have 3 things I need you to hear. There is a poll on Slido, so before you close out from upvoting all those great questions, I need you to quick switch to the polls tab and fill that out. We'll have those at every break, so I'll be reminding you every time. If you would like to sign up to go to the lab tours at lunchtime, this is your last chance, this break, and then we're going to close the registration. And finally, we are selling extra t-shirts. If you order t-shirts at registration, we're not selling your t-shirt, but you do need to go to the registration table to pick them up, please. But we do have a few extra that are left. It's first come, first serve. So you will go out to the t-shirt table. Dan should be sitting there, I believe. He's on his way out now. He's the tall guy with the cane that you've seen around this week. He will be selling them, so please go on out. They're $12 a piece. Come back at the top of the hour for another great panel. Thanks. Oh, does that work? Okay, guys, we're getting ready to start our next panel. It's the Technology Infusion panel, and I still need a couple of panelists. Oh, one more panelist. Jacob? So make your way to a chair or a table, wherever you're going to sit to watch this panel, please. And we're Jacob Matthews. Oh, he's here.
Yes, we're good.
Okay. All right, we have everybody. And I'm not going to delay too long because we want to give the panelists a lot of time to present their materials. And so I'm going to simply introduce Betsy Congdon. She is our APL LSIC Chief Technologist, and she is going to introduce the panelists. Thanks.
Hello. Yeah, there we go. So hello. We're going to pull on some of the threads that we've been seeing in the last 2 days, where we talk about how to take technology and make sure it's going to work. And now we're going to jump into interoperability. How do we take those technologies, have them work together? How do you think about technology infusion beyond just, you know, the one thing that maybe something was designed for initially and spread it out into the community? This is an amplifying effect where we can really use technology to create that sustained presence. So each of the panelists here are going to talk a little bit about their technology and some of the challenges and things that they are doing to support that ecosystem. And then we're going to have time for questions. So we hope we get some good questions on how you think about, these are all very kind of different technologies, but are amplifying each one. So first up, we have Pete Fiacco, and I practice that, Fiacco, talking to us about high performance space computing. So here we go. Is there a clicker? Okay.
Testing. Okay, good. We'll just tell you. Okay, I'm Pete Fiacco. I'm from Jet Propulsion Lab in Pasadena, California, and I'm part of the leadership team for something called the HPSC, which is the high performance space computer. So this is the next generation industry standard, we will say, replacement for, say, called the RAD 750 and all the computing stuff that we've been doing in the past. Next slide, please. So what is HPSC? So this is a NASA-funded program that's a public-private partnership between NASA, Microchip, and a number of other industry partners to drive hardware and software for our next-generation computing platforms, high-performance computing platforms. So the requirements were jointly developed by NASA, JPL, and Microchip. So the idea here, and you'll see in my slides, is this is not boutique, one-off space computing stuff. This is widely available, multiple product, complete ecosystem, hardware, software systems, and you'll see later on some of the details. The idea is to address NASA's requirements, JPL's requirements, government space, new space, and industrial applications, and you'll see avionics, all kinds of other things. From a kind of techie point of view, it's a fault-tolerant, radiation-tolerant, 10-core, RISC-V based SoC that's sort of one-stop shopping. There's a big Ethernet TSN switch integrated. There's security, industry standard interfaces. You'll see PCIe, CXL, Ethernet. The program will be delivering the SoC, the chips. There's actually 4 of them that have been announced. NASA funded 1, and then Microchip is doing derivative works. So there'll be a whole variety. They're all software and hardware compatible. We'll be providing evaluation boards, software stacks, dev modules for simulation, that kind of thing, education, training, application support. There's an entire ecosystem. I mentioned the industry ecosystem. We'll talk more about that. And why are we doing this? It's because the industry in general has been doing these boutique solutions and reinventing the wheel over and over and over again. And NASA thinks that there's a standard architecture here that we can drive into the industry and everybody can be more productive, standing on the shoulders of giants, say. So we don't have to keep rebuilding this stuff over and over again. Next slide, please. So here's just kind of a block diagram, some of the things that I talked about. Remember, this is kind of an edge compute kind of device. It's very high performance, so you can cluster these things and build supercomputers if you want. The 64-bit RISC cores have vector engines, so there's 8 512-bit vector engines included in the architecture, all supported under one software flow, so it's really nice. Anybody that's ever done GPUs and had to bring in that infrastructure, it's a little more complicated here. Think of it as the CPU development environment just works for the vector engine. All that optimization just happens automatically. There's a 240 gig Ethernet TSN is the reliability overlay for industry standard Ethernet. With what's called Rocky, which is RDMA support, all kinds of fault tolerance, radiation tolerance, all kinds of power control. It's something very unique for this industry. We can go about 2 orders of magnitude between the minimum power profile and the maximum power profile, the maximum performance and functionality profile. And there's defense grade security built in, which is something kind of new for the space thing, but very important as we're moving forward, very important for NASA. Nobody wants bad guys getting control of satellites and rovers and that kind of stuff. We'll have eval units at the end of Q1, calendar 25, and then fully flight qualified stuff about a year later. So that's our time frame. It's very, very close. We'll be taping out here by the end of the calendar year. In terms of fault tolerance, it's a highly fault tolerant system, which is exactly what we need for all the kinds of things that we do. And some of the folks here will be talking about, you know, rovers and autonomy and some of the important things that we're working on. And it's a kind of a layered approach, starting with radiation tolerant gates at the at the lowest level in the hardware, all the way up through application support for fault-tolerant applications. As an example, we have a multi-ported DRAM interface. It's kind of a weird graphic here, but we can lose an entire DRAM IC plus 4 additional independent faults in the DRAM interface, and the hardware can recover that without any software or system involvement. It's just completely automatic. That's the level of fault tolerance that we have. Next slide. A little bit about the architecture. Traditional SoC architecture, we have what's called the network on chip, which is the interconnect. It's a structured interconnect, very highly tolerant, fault tolerant, that connects all the major functional units. The application complex is the 64-bit, 8-core RISC-V with vector engines. There's a crypto accelerator, a whole bunch of I/O peripherals, the Ethernet switch, DDR interface, so on and so forth. So it's a complete system on a chip. I mentioned something about the power profile. It's completely user-defined. There's more than 70 what we call power regions on the chip, so you can turn those things on and off. So you can make trade-offs by defining software to tell the chip what functionality to turn on and what functionality to turn off. And that's dynamic, by the way. So you can turn things on and off as your system moves through its flight profile. You might need a lot of performance, a lot of capability in certain aspects of the flight. You might be in cruise, you can turn everything off and go into very low power modes and dynamically bring things up and down. Like I said, almost a 2x, almost 2 orders of magnitude difference between the lowest power mode and the highest power mode. I want to introduce something, so industry standard interfaces, right? Ethernet is the 800-pound gorilla for networking. Everybody knows that. But Ethernet isn't super reliable. So, and Ethernet doesn't work in real-time applications very well. So there's an industry standards IEEE 802 overlay called TSN, which provides these kinds of capabilities. So it's the deterministic real-time support stuff and the resilient packet redundancy, all kinds of things. So look into the TSN standard, and that's going to tell you about some of the new things. There's an avionics profile, which is being adopted not only by the space industry, but by the avionics industry, both government and commercial. So think, aircraft, military, variety of things. And Ethernet is going to be the standard. It's the standard in industry, high performance computing and so forth, and it's moving into the space avionics and so forth. It's more than just a chip, as I mentioned, it's a whole infrastructure, and it's all about layered standards. So on the board level, it's the SOSA or something called Space VPX. If you haven't heard of the Space VPX standard, I encourage you to go out and take a look at that, see what's going on in that standards body, it's not only standardizing individual cards, but it's standardizing interoperability. There's some folks here, Wes Powell from NASA, that are driving some of those standards and interoperability standards. And really the concept here is buy versus build, right? We don't want to have to build everything from scratch. It takes too long, it's too much risk, it's too much cost. The government doesn't want to fund that anymore, is the bottom line. So we have to find ways to be more efficient, and we're more efficient through standardization. We have a lot of partners. Here is a list of just 3 of the sort of SBC module partners that have publicly announced. There's somewhere between 90 and 100 companies that have signed up for early adopter status for HPSC. So they're in the pipeline for eval boards and silicon and so forth. So between 90 and 100 companies are currently engaged with HPSC today, and that list is growing. Here's a little bit more about the partner ecosystem. So if you look on the Microchip website, what you will see, they call this the PIC64. That's their Microchip's marketing name. They have 8-bit, 16-bit, 32, and 64-bit processors all under this PIC marketing name. So that's what you'll see. And Microchip is integrating this entire portfolio from small to large under the PIC portfolio, and the HPSC is the high end of that PIC64 portfolio. So the beauty of this is you'll be able to buy less expensive, lower performance, lower functionality product, maybe not flight qualified, just kind of commercial stuff you can put on your desk very inexpensively, do software and system development, and then move into the flight qualified versions that are obviously more expensive, but completely software and hardware compatible with what you've developed on your desktop or in your lab. And again, it's accelerating development and deployment, time to flight. Not only is it the SoC, but a lot of components that are required to build complete systems. So you're talking about DRAM, non-volatile memory, power components, that kind of thing. So the food chain, the ecosystem is very extensive. Software ecosystem is probably as important or more important than hardware. And so it's a complete industry standard open source software system. Development tools, state-of-the-art stuff. Can't get into a ton of detail here, but again, go to the Microchip website and you can see the entire hardware and software ecosystem, and it's evolving and growing every single day. Next slide. Where are we with the program? So we have the HPSC program, which is delivering all the things that I just mentioned. We're moving into phase 2, step 2, which is building test kits. So these are in form factor, 3U, 6U, and Space VPX, VNX form factor cards. So you'll be able to build systems. And then those systems are being infused into missions that I'll talk about one of those here. Next slide. I'm going quick. So I have 2 more slides. So one of the missions, one of the first missions that's going to be infused is a JPL system. So this is an intelligent landing system. So there's a super high-end LiDAR system, the HPSC single board computer, and then the LiDAR navigation algorithms. And one more slide. So this is a really interesting thing. LiDARs are very unique, as many of you know, because we've been using vision systems to land stuff on Mars and so on. It doesn't see through dust very well and requires illumination and other factors that limit where you can land and when you can land. So we think LiDAR, especially with high performance image processing, can solve some of these issues. And so the LiDAR operates this particular one in 3 different modes. Finding what's your altitude, doing map relative localization, and then actually landing with very fine granularity in an unknown space, right? Landing safely. To do this, you need not only the LiDAR capability for deriving the data, but you need the processing capability. That's what HPSC brings. So this is a good example of our first mission in fusion. And I think that's my last slide. So the summary, here's what HPSC is. It's a whole ecosystem, not just a chip. It's hardware, it's software. It's upward of 100 industry partners. And we'll be delivering prototypes at the end of Q1, calendar 25, and flight qualified stuff in 26. So reach out to us at JPL or to Microchip if this is interesting for you. And I think we have people talking about robotics here, which hopefully will be using HPSC.
Thank you. Next up, we have Bill Bluthman talking about the Viper mobility system.
Okay, thanks. I'm Bill Bluthman from NASA JSC. I'm going to talk a little bit about the mobility system. I'm going to expand that just a little bit, tell you a little bit more about the rover itself, then talk maybe a little bit about the hardware that Matt will talk about how we use, and then without even pre-coordinating, talk a little bit how our thermal system is designed kind of to do our version of surviving the night. In the last panel, Terry Fong discussed how much he appreciated the investment into what became Viper, and I would like to echo that. We haven't really been, we've been so down with our heads down trying to execute this with the ups and downs. It's hard to really kind of take a step back and kind of reflect on a lot of what got us here, and really a lot of got us here is really investment in both the technologies and the people that really developed the technologies. Terry mentioned some of the SBIR work, so I'll mention a few of them here. Maybe I'll start with them now, so in case I skip them before, I'll talk about some of the mobility work done by Proto Innovations. Sam Chandler is here somewhere. You should talk to him. They're doing really great work there in Pittsburgh. We'll talk about well, we're not going to talk about it in the talk, but our drill, one of our 4 instruments, is delivered by Honeybee Robotics, coming out of SBIR. And then our thermal management system was done by ACT in Pennsylvania, also done on an SBIR. So it's really, we've really had this opportunity to infuse a lot of tech. And again, when you're deep into it, you don't really think about it, but when you get on an airplane and have the opportunity to kind of reflect a little bit, there's really been a lot of benefit through the space tech investment in, again, on these very specific things, and then on a lot of the people. In fact, I'll talk a little bit about some of our mobility work in the year between the predecessor to Viper, Resource Prospector, and Viper. My Strucken mech lead, he worked on a ECI project, developed a prototype actuator for Gateway that really led to the foundation of what became the suspension on Viper. So there's really a lot of connections between Viper and tech that Space Tech has been investing in. Okay, go to the next, please. Okay, just a very quick overview of Viper. It's, I don't know, our OCOMS folks call it about the size of a golf cart. For a long time, I took offense to that, and then we built it, and I saw, yeah, it's about the size of a golf cart. Just to give you a kind of quick sense of where Viper is, kind of from a systems perspective, we're completely assembled. We've been through our environmentals. We've been through Vibe, completed TVAC about 6 weeks ago. The TVAC went very well, so it's come out really fully functional. So it's, if you want to think of it as prepared or tested through environments, it's got through and it's working well. A couple of the key things about Viper is it's going to the poles, so it's going to see the extreme environments. We've got to operate in permanently shadowed regions where the environment is on the order of 30 Kelvin. We've got to also survive. I think the agency calls survive the night. I think our version of that is survive in shadows of up to 50 hours. You've got this very harsh lighting that you'll see at the poles where it's on the horizon, so your cameras are either directly behind you, so everything is reflecting into the cameras, or it's right into your eyes. So there's those challenges, and there's been some data reflected that shows that there may be some differences in the trafficability at the poles that are maybe different from what we saw at Palo. That'll be a little bit softer, and you'll see how that is reflected in some of our design work. All right, next please. Yeah, a rover guy, I think of as a rover as a thing, but it really is just a instrument placer. So our 4 instruments on Viper is up front. Sticking out is the neutron spectrometer. It's really giving distribution of hydrogen across the surface, and then through the middle runs the honeybee drill. This is the 1 meter drill that was built on SBR I mentioned before. As it pulls up the regolith at 10 centimeters at a time, and there's 2 instruments up underneath, the MSO mass spectrometer and the near-infrared spectrometer that are analyzing the regolith as it comes up to get a kind of a depth, the material composition by depth, percentage of water by depth. Okay, we'll keep going here just to go on. So a little bit about mobility, kind of designed to manage, kind of really to add constraints to our diverse designers. Slopes up to 15 degrees, obstacles up to 15 centimeters. I think we'll see in the next slide we can do a little bit better than that, but that's really what we asked our designers to do. We designed this to a pretty long life, 20 kilometers, which is a pretty significant and aggressive mission. The wheel modules, there's 4 of them, has ability to drive, it has ability to steer, and it has ability to actuate each of the suspensions. Half a centimeters with grousers, goes about 20 centimeters per second. Steering doesn't fully actuate, but it does enough to allow us to do a little bit of crab walking with the ability to adjust the suspension all the way from almost to the ground up to about almost half a meter. And then we built the motor controllers in-house. They're all embedded in our warm box, so they're part of that, the system I'll talk about a little bit later that is stays warm when we are exposed to the night. Okay, go to the next, please. A little bit more about mobility. Our standard driving is, at least when we're in the sunlight, we drive omnidirectionally, where we point the corner of the solar array at the sun to maximize power generation. And then we have this ability to do hybrid mobility, which is really one of the key innovations. In fact, this is something we demonstrated back when we were doing work for Game Changers. So this is something developed under Game Changers that was kind of implemented as flight software on Viper, and I think you'll see that on the upper video here pretty shortly. It combines the ability to drive and steer and actuate the suspension. I think it's about to show right there. Yeah, so it does I don't know, some people call it army crawling, inchworming, crab walking. So it has the ability to do a little bit of crawling if you get into an embedded situation to get yourself out of a stuck situation. Again, some precision movements. And then at the bottom there, you can see the embedded slipping, where it's actually doing detecting it, so that to avoid yourself getting stuck, to get in this situation where you have to crab walk, you try to avoid that getting out. As our test platform, our version of a Scarecrow is McGrew, the Moon Gravity Representative Unit. It's our weight appropriate, so we fly at the lunar weight. So we basically strip away everything but a little bit of sheet metal structure and the wheel modules. And then we have the ability to add, basically violate that weight by adding cameras or lights to kind of bring in more fidelity in the rover, but have it actually be a little bit heavier, so it's a little bit less mobile, but it again brings a little bit more capability. We use this for engineering work, V&V work. We use it for exploring various engineering scenarios, various training scenarios, various ops scenarios. I think I've got, if you go to the next, I think I've got one of those scenarios, which are a handful of egress tests we've done over the years. Usually we've been doing these about once a year since 2021. The first one is very much focused on really defining what the lander to rover interface was. We learned a little bit about the rover, a little bit about the ramp design. We found probably a key thing there is we found that those browsers on the rovers were really very good at climbing anything they encountered. So we had to, working with Astrobotic, we cleaned up some of the sharps on those, and we were able to kind of fine tune some of that. We did more operations testing in 22 and 23, both engineering and really more formal type ops in 23, and then in 24, over the summer we did more V&V type work. We're actually testing the software during these egress scenarios. Okay, go to the next. Just a little bit about our gimbals. These are really sized to operate. Again, keep the gimbal pointed at the Earth, and what you're seeing here is the gimbal pointing it at the moon, kind of inverting it. I think when Andre is here, he's talking about when they are going to be zigging and zagging in the pressurized rover. This is our very low energy, very low speed version of that. But I think this is, I don't know, I don't see Andre with the bright lights, but I think this is what he was hinting at, the ability to be able to point while you're moving fast. So we've been thinking about this on Viper because we absolutely need to be able to point at the same time as we rove, because we have a high gain antenna. It's kind of we've got about 3.5 degree cone, so our gimbals are sized to support that, and then we're using our nav solution that Matt will talk about in the next talk to support that. Okay, go to the next. Again, just a little bit more about the nav hardware. Matt's going to go into more depth of a really more interesting part of it, how we're using it. Go to the next. 8 cameras across the vehicle. There's 2 nav cams that we're using for for really stereo reconstruction. There's 4 HAZ cams that are in the wheel wells that are using for looking at the wheels, and then there's 2 AF cams looking through the rear solar panel to give some situational awareness behind the vehicle. The HAZ cams and AF cams are very wide field of view. The nav cams are I guess still pretty wide, but not the super wide that the others are. Go to the next. The lights, when we started this, we looked around for just an off-the-shelf solution, didn't really find any, so we built these in-house. There's kind of the headlights that are on outside, just outside the nav cams, and then there's a series of 6 of them around underneath the rover for giving situational awareness, really working in tandem with the HAZ cams to really give the driver's situational awareness underneath the vehicle, so to be able to see the rocks up underneath. Okay, go to the next. And then Star Tracker, this is the first use of a Star Tracker for a planetary rover. Again, it gives us the benefits of giving us very accurate matching of the stars, very accurate orientation. It happens very quick. It works well in the dark. So it's a part of that broader nav solution that Matt will talk about next. Okay, and then kind of a little bit of a divergence, talk a little bit about our thermal system, kind of going a little bit off the mobility topic, but it's all supporting that. So Viper's got a couple challenges. It's got to be able to operate kind of in a wide variety of things, and it has to really operate to get full success across a couple lunar days. So that means be able to park someplace high, survive, we'll say in shadow, both the shadow of the sun and the shadow of calm. So it has to be able to operate in a quiescent state for 14 days or so out of communications, and then some period of those 14 days in the dark. Then it has to operate in the extreme cold of the permanently shadowed region. And then, of course, it has to operate in the sunlight. The environment is not too cold, but once without the in the vacuum, once the sun hits the components, they do get warm. So you do have to kind of treat it like you're going to get it very hot and you get it very cold. So the challenge, again, our challenge on the thermal system is to you got to be able to, when you're hot, you got to get the heat out, but when you're cold, you got to be able to hold the heat in. So we came up with a kind of with a system that had the ability to kind of turn on and off the radiators. We had a multi-layered MLI design. I think one of our thermal leads called it kind of a Russian doll type experiment where we had layer upon MLI, layers upon layers upon layers. And then to kind of handle our hibernation, what we call our hibernation period, our time in shadow. We had some specialized circuitry that went into our integrated avionics unit that allowed us to go into very low power mode, running only survival heaters in this 1.5 watt timer, effectively, that would wake us up after some preordained period, in the case of about 50 hours. Okay, and go to the next. Okay, I think this maybe is my last one. So again, if you look at Viper, it's really defined by the solar panels, the radiators, but really, I hate to say this is a rover guy, but really Viper is just a thermal system with wheels, because so much of what we've done is to survive this time in the shadow. It really drove so much of our design, and if you pull off the solar panels, it really is this warm box and the ability to mount the avionics to the warm box, the ability to get the heat out of the warm box through a series of looped heat pipes to the radiators, the ability to shut that off in a very passive sense through a thermal control valve, plus kind of all the smart things you do to isolate the things that you allow to go cold, so that you're not leaking too much heat. The ability to let the solar arrays go cold, the radiators go cold. We did some of the smart design and the mechanisms to allow the thermal expansion and contraction, so that you didn't have to throw heaters everywhere and burn all your heat in the extremities. And there's that. So coming out of TVAC, again, our requirements are about 50 hours. We ran 57 hours in hibernation, so survived that 50 hours plus. We're really early in the correlation of the models. There was a little bit difference in the environment, so it's going to be 50 hours give or take. So kind of as that continues to evolve, we'll kind of keep everybody up to date. I think a few of us were talking at dinner last night about ISIS. I think our thermal team is going to maybe put in a handful of abstracts at ISIS, so probably more of information about the thermal system will be coming out going forward. And I think the last slide is really just kind of really where I started with is, we kind of did what you do. We bought, we adapted, and we developed tech when we did, and we had the ability to develop tech because of the great investment out of space tech in both the hardware, the commercial industry, and the people. And that's it. Thank you.
Thank you so much. Next up, we have Matthew Deans, as has been introduced already, to talk about the Viper navigation system.
I'm green. Okay, thank you. Thank you. My name is Matthew Deans. I'm at NASA Ames Research Center. If any of you have dealt with the SBIR program, you probably have heard of Matthew Deans from Glenn Research Center. We get each other's email all the time. We're on a first name basis. Could you go to my first slide? Okay, so Bill covered most of the hardware here, but I'll just point out a couple components that are critical to the navigation capability. There are the cameras and lights, of course, the star tracker, which gives us instantaneous, really good orientation estimates from the star field. It only works when the rover's sitting still, though, so we have to also have an inertial measurement unit on board that helps with orientation estimation while the rover is moving. And there are wheel and joint encoders, so we get feedback about what the steering and propulsion and suspension are doing all the time. And we have a couple of control units for the lights and the cameras, of course, to make all that work. Next slide, please. The software is, there's sort of several key components to the software for Viper. One being the flight software. That's everything that runs on board. There's a Rad750 and an SP0 on board Viper, and they have some of the functions are split up across which one of those processors is more amenable to which processes. It provides all the low-level hardware interfaces and mobility control, relative localization on board. The flight software has to close the loop, so that when we send commands to the vehicle to drive to a waypoint, it's the flight software control system that closes a loop on the rover driving to that waypoint. There's too much latency in the system for us to drive this rover using rate control. So think of like a gas pedal and a steering wheel or a joystick. We can't do that. There's too much latency in the system. So we use a waypoint style driving. And the flight software has to close the loop, and navigation is a key piece of closing that loop. And then we have the what we call ground software for Viper. Because of the low latency and relative high bandwidth to talk directly to the moon from Earth, we have the opportunity to take some of the more complex, higher level functions that need a lot more computing. We don't have HPSC yet for Viper, so we send a lot of data to the ground, and we use commodity hardware to do some of the heavier computations. And also because of that, we get to leverage other software frameworks like ROS2 that we've been using for a lot of our middleware and some of our capabilities. And it's just generally an easier computing environment for us to do our development and testing and verification. And then finally, Terry Fong talked already about the rover simulator, so I won't get into that too much here. Next slide, please. So Bill and I don't always give these talks back to back, so we have the same slide. I'll just point out again that one of the key needs for the navigation system is to always know the rover's orientation well enough to use the gimbal to point the high gain antenna back at a DSN ground complex. That is to make sure that we maintain a consistent connection and maintain a high quality, high bandwidth connection, because we are going to drive this, we would be driving this thing 24/7, constant commands, constant telemetry. Even losing that connection would require reacquiring a signal and reestablishing comms, so we don't want to do that. And again, this was a test where we reversed the roles of the moon and Earth. This is the rover on the Earth pointing at the moon. We have a camera in the place of the high gain antenna, so we can see exactly the pointing accuracy of the high gain antenna, even as the rover drives, over obstacles. The suspension's moving, the rover's bouncing, but all that is measured and estimated by the IMU and the flight software and used to keep the antenna pointed accurately. Next slide, please. So on board the rover, we have one of the flight software apps. The mnemonic for it is PEST, but it's position estimation. This is the first place that a lot of the onboard hardware gets integrated into a continuous position and orientation estimate. Good enough for the flight software, good enough for the rover to get to the waypoints that the operators are commanding. We do accumulate some error over time. This is a hard, rigid wheel moving in a granular material, so the wheel slip is to be expected. We don't have a great way of quantifying the amount of slip all the time in flight software. There are abilities to detect excessive slip conditions. We don't want to get the rover stuck or horribly off track, so there is some ability on board to detect high slip conditions and basically stop driving and send down like an error message to the ground saying the rover is slipping too much. But we have to make up for, over the long haul, we have to make up for that wheel slip on the ground software. Next slide. So in the ground software, RGSW, it's a bunch of robotics capabilities that we deliver and integrate into the GDS, and they become part of the overall ground segment for Viper. I'm going to get into some of the key functions that are part of the navigation capabilities. Next slide. So to start with, and again, Terry Fong mentioned this earlier in the Proving Grounds panel, we start with what we call a shape from shading, DEM. This is because this goes beyond the resolution available from just stereo processing of orbital imagery. This uses photocalorimetry to estimate the slope of the terrain at the pixel resolution of the original NAC imagery, and with a whole bunch of images of the same scene under different lighting conditions, we can back out slopes, and we can integrate those out into an elevation model. And this is a key input product to the ground software navigation capability. Next slide. So from the images that come from the cameras, one of the first things that we do is process those into stereo point clouds. We recover the shape of the terrain in front of the vehicle. Again, hearkening back to the proving ground panel, this is imagery across the top row, imagery from our lunar lab. This is a regolith simulant test bed. We have flight engineering unit cameras with flight engineering unit lenses on them, calibrated, and we take images in the lab with controlled, lunar-like lighting, and we are here trying to verify that we get good enough quality stereo reconstructions of the terrain, and also point out that one of the unique things about this algorithm is that we measure not just the horizontal disparity that helps you triangulate distance, but we also measure what we call vertical disparity, because we're very worried about the harsh thermal environment and the thermal differences for Viper, making things go out of skew out of alignment, and we would want to be able to detect that so we can do something about it. And then across the bottom row, that's images from our sim, and the same disparity and point clouds from that. And this, we use both of these kinds of proving grounds to do our software V&V. Next slide. For hazard detection, we have an operator in the loop at all times. So Viper, it autonomously executes the commanded waypoint, but it does not do its own route finding or path planning or decision making about what those waypoints should be. And so if you'll click one more time, one of the key decision support products to the operator is a hazard detection output. This is a very similar algorithm that runs on board some of our test rovers that we would drive around in a terrestrial setting autonomously, but for Viper, we integrated that capability as a decision support tool for an operator. So the operator is the one who ultimately looks at those maps and decides what's safe and what's the best way forward, and then controls the rover by sending waypoints to areas that are hazard-free. Next slide. Visual odometry is one of the key ways that we make up for the wheel slip that we expect. There are 2D image matching methods and 3D terrain shape matching methods that help us recover the actual vehicle motion and how it differs from the estimate on board that doesn't take advantage of vision. And this is how we correct for the wheel slip. Next slide. And then even with visual odometry, that greatly reduces the rate at which you accumulate error, but it does not completely eliminate the accumulation of error over time. And so every once in a while, we would expect to use rover-derived imagery to build up a model of the shape of the terrain all around the vehicle, and then align that with that high-resolution shape from shading DEM I alluded to earlier. And this helps us to pinpoint the location of the vehicle on that DEM. And one of the really critical things about that is that for Viper, the science team has models of where we would expect ice to be, and those models of thermal stability and ice retention are based on high-resolution shape models of the terrain. And so our terrain matching global position estimate is directly aligned with the models that the science team uses for where they expect to find ice. So even if we have errors in our map with respect to the actual, say, latitude and longitude coordinates, we are actually localizing to the thing that is modeling the ice stability. And next slide. And this is my last slide. All these things, the visual odometry, the flight software pose estimates, the terrain registration, they all go into this data fusion algorithm that's constantly taking all the available information and building an estimate of not just where the rover is now, but where the rover has been. Because we don't just care about moving forward, we care about producing high quality maps of the data we've been collecting the whole time that we're driving. And so there's this critical data fusion piece where we are constantly maintaining and updating this factor graph and using it to always produce a current best estimate of everything. And I didn't think to put a conclusion slide, so that's my last slide.
Thank you very much. Finally, we have Jacob Matthews talking about commercial radioisotope power.
Thank you, Betsy, and thank you, Jamie Porter and the entire team. I thought this was a great event, so thank you for putting on this excellent meeting. I think I am the last presentation between you and lunch, so I will try to go as slow as possible. Hi everyone, my name is Jake Matthews, co-founder and chief technology officer of Xeno Power Systems, and we are very focused on survival and operation through the lunar night. Next slide, please. And this, of course, is the top shortfall as identified by the Civil Space Shortfalls rankings. But if you look at the top 5, 6, really, it's all really revolving around either sustainability, sustained presence on the moon, and how do we get the power to do that. But we've done this before. The Surveyor 7 mission, the picture there, it demonstrated that if you add heat to your electronics, that they can survive through a lunar night. Now, it had degraded performance, might not have been scalable, so Apollo missions quickly transitioned to radioisotope power systems. There was a radioisotope power system on every Apollo mission to enable long endurance science on the moon. So we've done this before. And recently we're seeing internationally, globally, people choose, governments choose this as the way to do a sustained presence on the moon for their individual programs. Next slide. Of course, China has put a rover that's been operating on the far side of the moon. Just recently, ISRA had put it wasn't on the lander, but it was on the orbiter to demonstrate this radioisotope power system technology, anticipate that being on the next landed mission. And recently, Argonaut has baselined a radioisotope power system starting in 2031. Every 2 years, we'll have a radioisotope power system on board to enable, survive, operate through the lunar night technologies. So, as the United States domestically, we started this. Why aren't we doing this? Well, there's an easy answer to that question. These systems were always built by government for government, and we want to do a lot of infrastructure development on the moon. And right now, that's just not the scale of the current systems. We need other systems, other providers of these systems to really enable the infrastructure development that we need on the moon if we're looking to do the kinds of things that we want to do, both commercial operations and science. So next slide. So that's where Xeno Power comes in. We build radioisotope power systems. That is nuclear technology. We're not a reactor. It's usually watts to kilowatts of heat. And that's through the decay of an unstable material. It's not tied to the sun. It just works anywhere. So it's a robust, long endurance power source. Think the Voyager space probes outside of the solar system, 50 years later, still providing power for those science missions, enabling just a fundamental change in the understanding of the universe because of these systems. We are a growing company. We're a startup based out of DC and Seattle. And we have contracts to develop these systems right now. It's a very exciting time for us. And really, it's 3 major anchor customers, government customers. We have a Space Force contract. We're not just for space. We can also do anywhere where power is hard, so like the seabed. So we have a Navy contract to do a system on the seabed. But also a NASA Tipping Point Award that we have some great stakeholders and some great collaborators on all of these contracts. And I'll dig into those contracts a little bit more later. We have demonstrated this technology that I'll talk about as well. We did a demonstration heat source at Pacific Northwest National Lab in October 2023 that really demonstrated our isotope that we can design this and shield this in a different way that could bring the mass of these systems down. And that's important because we are using a much more affordable and abundant isotope than what has been used before. Typically, it's been plutonium-238. It's a fantastic isotope, very high performance. It's just not that abundant. We need something more abundant. So Strontium-90, over 100 of these systems have been deployed terrestrially, but typically they've been too heavy to send to space. So we're trying to change that, find this abundant isotope, and send it to space because it's actually light enough to do now. And we've benchmarked our models, both radiation and thermal models, using this test at Pacific Northwest National Laboratory. And finally, we've also, in January of this year, announced that we've secured our fuel and facilities to build our heat sources for roughly the first 10 systems by recycling some of those old RTGs that I mentioned earlier. And we're also working with Westinghouse as our facility partner to build these systems for Space Force, Navy, and NASA. Next slide. So when I say radioisotope power system, what do I mean? That to me is a suite of 3 technologies. The first being a radioisotope heater unit, or a RHU. That just provides heat. So you can put it next to your electronics in very dark, cold places and shut everything else down, but it'll keep it warm enough for those electronics to survive. But we don't want to just survive, in places like, on the lunar surface or in deep space. We also want to operate there eventually as well. So RTGs is typically what has been thought of as a radioisotope power system. That's the Voyager space probe, all the Apollo missions, as well as most recently the Perseverance rover. And these use, the heat provided from the radioisotopes is turned into electricity through a solid-state device known as a thermoelectric converter. And that is a solid state, so there's no moving pieces, and it's very reliable, just works, and as illustrated by Voyager, works for decades potentially. The one drawback is it's not very efficient, so about 5% efficiency for these systems. So as we want to scale these, we want to provide more power to get towards thriving and provide more power for the science and commercial operations that we want to do. Our answer for getting that efficiency up is Stirling engines, and that has been developed by NASA for decades. Put a lot of smart people on this problem, and for us, we want to use all of that and incorporate it for lower design life, so not 17-year missions, which is typical of a plutonium-238 device, but maybe a 5 to 10-year mission that would be what we would aim for a strontium-90 system. So that gets the efficiency up to 20 to 30%. Next slide. So our contracts. So we have 3 contracts that we're executing on right now. The first one, as you can see, is with the Navy, and it's for seabed power. And that is a strontium-90 radioisotope Stirling electric generator. Looking to deploy that for testing 2026, maybe late 2025. Now, I'm going to come back to that one. Why am I telling you about an undersea system at an obvious space conference? I'll come back to that one. The next one is for the Space Force. We have an strontium-90 RTG. It's for space applications, and we look to have that flight ready by 2026, 2027, and really that can be adapted for other applications as well. Just take the power system. That's actually a full satellite platform. We can take that out and put it potentially into another platform for use in other applications. And then finally, our NASA Tipping Point Award that we call Project Harmonia is a different isotope. We're actually branching out from just strontium-90. We also are working with americium-241 as well. And that is also a radioisotope Stirling generator. So we are using lessons learned from our depth contract from the seabed to apply that to space applications where there's overlap. And there's a decent amount of overlap as well. And that helps buy down the risk for this future system for NASA and for lunar applications. Next slide. So like I said, we've secured our initial fuel and facilities using these old RTGs. We have control of that asset right now, and there is 3,000 watts of heat in it. So we can recycle that for applications starting this decade. We're also working on the supply chain for americium-241. A tipping point award is only TRL 3 to TRL 6, so it's not really required for nuclear systems, but we're leaning forward on trying to develop that supply chain. And then finally, I'd already mentioned facilities with Westinghouse. We have the facilities required to handle this nuclear material safely and produce these systems and deliver them for customers. Next slide. I'm going to touch on safety. I will mention, safety is of course very important. I'm going to touch on our approach to it. I'm sure as there should be many questions. During the breakout session, I'll have our Director of Space and Planetary Regulation who can talk for days about this. And there's a lot of nuances, so I don't want to miss them. So if you have any safety questions, please join the breakout session as well. But our approach is really codifying something that has been done with all of these space nuclear systems in the past. That's really a defense in depth. So looking at safe operations for these systems, we're not going to do a mission that could potentially be dangerous and result in a release of nuclear material. We look at the containment. So the core of the technology is basically hot rocks in a box. Most of our important engineering comes in the containment vessel for that nuclear material to make sure that in very extreme engineering conditions that we do not lose containment of nuclear material, including to impact with the Earth during a launch anomaly. But even if you do, even if you assume that we lose containment, the radioisotope itself is engineered for safety in that it is not soluble in water. So it's not very mobile in the environment, and it'll have less effect on the human body or the environment if it does come in contact with it. And then finally, designing with the end in mind with contingency operations so that if there is any of this, which is very unlikely, that we will be very quick to clean this up and make sure that it does not affect any humans or the environment. Next slide. So I want to end on what we aim to do here is typically radioisotope power systems have been on the flagship missions that have delivered marquee science for NASA over decades, but it's just been at a flagship level price. What we would like to do is deliver that flagship level science at a fraction of the flagship level price, and for the first time be able to be a commercial company delivering these systems to government that can really buy down the price and the risk for NASA as well. And also, for the first time, be able to give these systems for use by commercial. As the moon and space in general begins to be more and more commercialized and more commercial actors out there, they're going to want to do things that survive through the lunar night, that build off of the infrastructure on the moon, and are able to do much more exciting things in the coming decades. And we think that's only enabled through long endurance infrastructure that you can get through radioisotope power system and integrate it into all of these very important infrastructure assets on the moon. With that, I'll pause for any questions. Thank you.
Thank you. So there's some great questions on the Slido. As Jacob already mentioned, there is a breakout session this afternoon where these folks will be present. So some of the questions are fairly specific, but I'm going to kind of target in on ones that multiple panelists can answer. So let's start with talking a little bit about, we're talking about technology and fusion. What are the first steps that you guys are thinking of in order to take your technology and have it adapted into a similar system or utilized by a commercial company, that sort of thing?
See if I can make this work. So HPSC we want to infuse high performance computing into all these space missions. If I come from the industry side of things, so high performance, all the GPU, TPU stuff and networking storage that you see running around doing AI. That's my background. I'm used to infusing technology continuously and aggressively. It's different than the space community in my experience so far. If you look at what technology we talked about, RAD 750, that's a 30-year-old CPU that we're using to run state-of-the-art rovers. It's pretty frustrating for these guys because they can't run you see all the different advanced algorithms, right? They're having to download data to Earth to do the computing on Earth. I'm sure he would be rather doing the computing on the rover in real time, running around. I wrote a paper for a university recently where I compared kind of rovers, and I looked at Apollo 17 and the way the astronauts drove the lunar rover back in the 70s, right? They're driving that thing like it's a Corvette. And you compare that to state-of-the-art today, some of the folks that have been talking about here, or the Mars rover, there's many orders of magnitude difference in the speed at which these autonomous rovers run versus what the astronauts could do. So I think as a community, and I've talked to a couple of the universities, a lot of grad students, and I've given them the challenge, right? How do you make a robot drive like an astronaut? And then I show them the Apollo 17 pictures, right? And these guys are driving around like crazy. How can you make a robot drive that fast and that accurately and cover that much ground and do that much science or whatever? That's really what we need to do. In order to do that, we need super capable processing, and we need software and algorithms. We need energy, right? So this panel, right, kind of covers the whole soup to nuts thing. Now, how do we get that implemented into missions? That's a big problem. We have this HPSC technology, but as a community, I had somebody at one of our major partners, executive in the engineering organization, he told me, He goes, Pete, you realize our engagement with HPSC, this is the first time we've engaged with a technology that's pre-silicon. He said, we usually don't do anything until it's been in production for 5 years or 10 years or something, right? Because we're very risk adverse. We don't know how to deal with that. So that's really the infusion problem right here, is there's this technology chasm, right? Everybody's seen these charts about the valley of despair or whatever for managing new technologies. This is really what we're facing right now, right? We have all these great technologies, and how do we get them infused into flight programs, and what are the steps to make that happen, and to make that happen quickly and cost effectively. You know, NASA is not going to be able to fund things, and they're not going to be just writing checks like they have been in the past 20, 30 years. Everything is changing. We as an industry need to be more efficient. We need to do things faster, cheaper, better. And that's really the key here, right, is getting these technologies into these roadmaps efficiently and quickly. And it may mean taking more risk. And I think we're seeing that, especially in the lunar thing, right? I mean, we're seeing things being sent to the moon, and they may not be what we would call 100% successful mission. We had a thing land on the moon not so long ago, and it, you know, tipped over or whatever. But we learned a lot about what we need to do to be able to land on the moon in those conditions. And I think the next time it's going to be much better and much more productive and much more perfect. I think SpaceX is a perfect example of that. I'm sure all of us have seen over the last 10 years the SpaceX stuff, right, blowing up. And then they figure out that problem, and then they do another launch. And the idea is to be able to iterate quickly and successfully, and I think everybody saw, you know, how SpaceX is doing very well in some of their advanced technology. But how do we cross that chasm? How do we, as an industry, accept the mindset of more risk? How do we do that effectively, cost effectively, and schedule effectively? It's really difficult, but we have to solve this problem. Otherwise, we're not going to be relevant as an industry, because somebody else will figure out how to solve it, right, and make it happen. So anyway, that's my challenge to the industry, right? How do we do this faster, better, more cost effectively?
Jacob, you have anything you want to add?
Yeah, no, great points. I want to piggyback on the computing. I think it's a game changer, especially for us, because we're an artificial radiation source on the moon, which is a very radioactive place to begin with. And I think as we look forward to long endurance infrastructure, you need interoperability with the electronics and all of the components that are going to not be designed to last just 2 weeks, but years, hopefully. So you need a lot of interoperability to gain that kind of data on the components that will really drive this type of hardware. Interoperability is important for us. It's written into our Harmonia contract for the NASA tipping point, because I'm going to take a wild guess that everyone out in the audience doesn't actually want to do all the paperwork to own nuclear material. We'll do that. So we'll take that, but that means we are going to do something like a charging station on the moon. So how do we make it interoperable for all players that want to have heat, have power, have potentially data and services tied to that you can get access to that? How do I protect it from potentially bad actors that didn't pay for that service? Interoperability is a hard problem, but it's a very important problem, and I think I'd love to talk about it more.
Yeah, the one of the things about interoperability that comes up is we start thinking about future-proofing. So we're talking about how we have these technologies that might be 30 years old and they're on the moon. That you hope that as you build out an infrastructure and you have sustained presence on the moon, that these things will get used for a long time, maybe beyond the life that they're thinking. So how do you think about kind of future-proofing and preparing for a future or a mission that you might not actually know right now?
Software-defined functionality. That's the key. You'll see it in the automotive industry today, right? So I know some of you may not be great on, say, the Tesla software updates or whatever, but that's how it has to be done, right? It's very difficult to replace hardware once it's placed on the moon. So once we have that hardware there, we need a way to reliably add functionality, fix bugs, and add functionality, on site. So software-defined functionality. Everybody out there, we should all be thinking about software.
I agree with that. I mean, something modular that you can update over time. I mean, that just increases your capabilities over time. I think the way I would think about it is we're in a chicken and the egg. We don't know. We're on the the cutting edge of what's possible. So we don't know really what our customers want, and so we're asking what do you want, and they're turning back to us and what is possible. So at some point there needs to be a leap of faith to get out there, and you have to at some point just say, we might be wrong on this first one, but we'll be nimble enough to adapt to that very quickly. And that comes down to, I think this is part of a discussion about, the project management triad between, either your technology risk, your schedule risk, or your cost risk. And, to at some point manage that, you have to just set a schedule of we are going to launch what we have right now. It might, we will try to mitigate some of those risks on if it fails, but we are going to do that because, as has been stated before, we learn so much by testing and by, and not, well, I'm not saying don't measure twice and cut once, but analysis can only get you so far. You learn so much from actually doing it. And the fact that we iterate and something does get old is a good thing. That means we're growing our capabilities and that we learn from something and we can make it better. So we can't be too afraid of being, of something eventually getting old. That's a good sign that we're progressing our capabilities and being able to do cooler science and cooler commercial operations on the moon.
Bill and Matt, you both lived, evolution of things happening while technology might have progressed maybe terrestrially while you're adapting a system, for the moon. Can you tell us a little bit about some lessons that you learned through that process of how do you think about new things? You mentioned we couldn't find this. We had to, develop our own. Can you give us some lessons learned from that?
Sure. So what we found is, we had a number of different approaches where sometimes we had, a lot of it was about the person, right? Or about the people kind of were bringing it. Some people just had this natural act who had done it in the past, and they could take their technology and, take it through concept, design, tests, and kind of integrate it into the vehicle. We had others that really we had to pair with people that were, had more of a background in really more spacecraft design. So we kind of had different approaches as we went through that, and it really varied by technology, by person bringing the technology, by organization bringing the technology.
Great, and we're almost to lunch. I'm sure everybody wants to eat, but I'll wrap up with this one question. This is specifically asking about some of the progress in quantum fault tolerant systems, but I'll open it up a little bit. Obviously, we have research happening in academia that might break new ground and maybe enable something that's, in the future. How do we infuse that faster? How do we kind of bridge that gap between academia and things that are happening to hardware on, on the lunar surface? Hard question.
I'm not sure if this addresses this particular, quantum-related issue, but more generally, how does new technology get infused into these programs? And one of the things we're doing on HPSC is we have, I called it public-private partnership. So this is NASA, JPL, Caltech's associated with that, a number of other, university and research-oriented organizations. And they were involved in, from day one, with driving specifications and requirements. And again, many of the university connections that we have today have to do with algorithm development, and that drives software. So, I'm not sure I have a silver bullet for this, but there's very specific things that I think we can do to drive that development pipeline more effectively.
Having those partnerships,
yeah,
obviously
so partnerships, get involved early, and then have flexibility.
Thank the panel one more time, please. And if you want more information, there is a breakout panel. There's actually one in each session. So, okay, so before you break for lunch, there's a Slido poll. So I brought my phone up. This is on the questions and answers. You just click on the poll and you can answer the questions. We would love to have your feedback. The lunches, again, are in the hallway just like yesterday. If you know what you want, what you ordered, just go straight to the lunches and grab your lunch. I have a hint for you. If you don't remember what you ordered, if you go and Google on your email, LSIC meetings team, you'll find your email receipt. It's got the QR code at the top, and at the very bottom, it'll tell you what you ordered on November 14th. So then you can skip the line to find out what you got. If you can't figure out what you got, there will be people out there assisting with lunch selections. If you're going on a lab tour, meet out on the lanai, sort of right behind the UNLV booth, and we will hold your lunch for when you return. And finally, student lunches, just grab a drink and go to room 208A at 12:20. Your lunches should be separated out to there. So, okay, great. And we'll see everybody back here at 1:40 to talk about space sustainability. Thanks. Sorry, everybody, I forgot one thing. There are networking rooms. They're listed up here, so you can go and talk to your friends in your favorite focus area. Thanks.